have your lecture notes. Still the same lecture, Kalman filter, but this part I'm going to derive. Hopefully today we'll finish deriving the entire Kalman filter. Hopefully, I'm not sure. Okay, let's have a quick recall. Although we haven't learned Kalman filter yet, I keep telling you there's few facts you should have in mind while you are learning or reviewing probability. The first one is Kalman filter does the same thing like a Lundberg observer. Okay, the input and output of Kalman filter. This is Y, this is U, and I want to have my state estimate. All right, you have to have your problem in mind, okay? And now instead of using Lundberg observer, difference between these two are Kalman filter assumes a stochastic linear system model that we are going to discuss a little bit in more details later today. And that's the modeling assumption different. The second one is it's optimal, okay? It's optimal in certain sense. And a solution I already tell you, Kalman filter is just this. What is it? It's a conditional expectation. Kalman filter is nothing but a conditional expectation. Okay. Why is that? Today we're going to answer these two, then we derive the entire Kalman filter. First of all, why this guy is optimal? Why conditional expectation is optimal? In what sense it's optimal? And how do we derive those conditional expectation formulas based on the modeling assumption? That's what our goal is today. Okay, to understand this, you should have to understand the so-called minimum mean squared estimation, MMSE. Have any one of you heard about this or learned this before? Did you take machine learning class? Yes? Did you learn this?
Maybe
another name. Okay. Did you learn Gaussian random vectors or random variables? Random vector, I think. Did you learn Gaussian random vectors in the machine learning class?
The first part of all about
Oh, okay. Maybe many of you haven't taken machine learning class. That's another core course you have to take. Okay, let's direct jump to the minimum mean square estimation. All right, let's jump out of the box. Let's think in general. We have a general problem. Suppose we want to estimate the value of a hidden random variable. What do I mean by hidden? Exactly, so I cannot measure it. Okay, I can only guess its value from another observation that I can directly measure. So based on, I want to estimate the value of this x based on relations, observations of a related vector y. Okay, that's roughly almost all estimation problem. Okay, let me repeat. So you can think of all of this estimation problem, even majority of machine learning problem is trying to solve this problem. Let's think you have the famous image net. Okay, you have billions or millions of pictures and you want to tell whether it's dog or a cat. Okay, what are the hidden variables you're trying to estimate? It's a label. So whether this guy is cat or dog. Okay, so it's x equal to 0 if it is a cat, x equal to 1 it is a dog, let's say, right? So you want to use your measurement y, which is all the pixels of all those images, to best estimate the value of x. The x is 0 means cat, x is 1 is dog. Did I repeat the same order or not? I forgot. Anyway, so that makes sense. You don't know based on the observation. It doesn't tell you this hidden variable x, which is the label of this picture, but you can try to estimate it from images. So the entire neural network is trying to give you a so-called best classifier, right? So you're doing estimation in that case. Your face recognition, whether it's you or not. That's exactly estimation problem. So majority of the things you're dealing with in machine learning or in signal processing, all of them, most of them can be thought of as an estimation problem of something you want to use measurement from Y to estimate something hidden that you want to know. Okay, are you with me? Okay, so this is very generic, general class of problems. And I'm not sure whether how does this sound like, does this sound similar to the least square problem we described to you before? We want to estimate hidden variable theta from measurement, and we don't directly measure theta. So this is also an estimation problem, if you think it's a least square problem, but it's just a deterministic estimation problem. All right, so now in this lecture, we are going to take a little bit jump. We don't think about them as a deterministic relation. So this is almost like, I think Y is a linear, is a matrix times theta. And this matrix is deterministic, right? We're having an almost deterministic relation between the hidden variable and the measurement. Now, for machine learning or for a Kalman filter, for the things like this, we are going to take, I think, a much more powerful viewpoint, which is probabilistic relation. How these two are related? If you tell me the distribution, joint distribution, then we know exactly how they are related. So typically the relation between the hidden variable and the Y can be described by a probability. This is probability, this is the PDF, right? Probability density function, or PMF, right? Let's say Pij, if there's discrete values, that is PMF, probability mass function. If you tell me these two joint distribution, this is the joint distribution of these two random vectors or random variables, then I know exactly how they are related. At least this is the knowledge in our mind, how they're related, okay? Now I'm going to define a so-called estimator. So estimator is this block. You send me an input to the block, which is a measurement. I tell you my best guess. In the image recognition case, this will be a picture. This guy will be dog or cat. Okay? You write a function in Python, MATLAB, C++, whatever, and the function take input of the image, and output tell you, okay, this is my best guess, which is, I will tell you this is dog, maybe wrong, that's fine. Okay, I can, so for example, I can say a simpler example that I like temperature, okay? Because I love Shenzhen's temperature so much. So let's say Shenzhen temperature, let's say Y, and this Y typically will have a number. The small y is deterministic, okay? It's a number. I see a number today. I'm not sure whether today is 26 or not. Maybe colder than that, cooler than that, okay? Then the output could be maybe it's Guangzhou's temperature, right? But I can say this output is phi, a function of y. Let's just say this is y minus 0.5. I think, I'm not sure whether that's true, but Guangzhou is half degree cooler than Shenzhen. Okay, that's my knowledge. Okay, I can be wrong, but that's fine. This will give me an estimator of Guangzhou's temperature, x hat, in relation to Shenzhen temperature, which is what I can directly measure here. Okay, because for example, I can only measure my current location temperature here in SUSTech. Then I want to use that measurement to guess Suppose I don't have internet, okay? I can guess Guangzhou's temperature today, and my guess, the rule of this guess is y minus 0.5. Okay, in this case, my function will tell me, okay, it's 25.5. What I'm talking about is that estimator just maps the measurement from so just map the measurement y to the hidden variable guess. You don't know exactly what the hidden variable is. You cannot directly measure them. You just guess them, right? This is a guess. It could be good, it could be bad, right? So maybe Yuntian will say Vy is 2 times y. That will be 52 degrees. You think that's ridiculous, it's wrong, right? But he can argue that he thinks today is, he knows something that we don't know, right? As a Mason probabilities, that's something that about our own kind of belief about uncertainties, okay? So we have to have a rule or criteria to determine what estimate is good. Is this good? Or this one is, which one is good? Which one is better? Most of you think this one is better based on common sense, right? But common sense doesn't mean anything. Okay? So everyone believes something is like that. It doesn't mean it's right or wrong. We have to have a scientific way to determine what's right and what's bad. Okay? Yeah, common sense is just complete. You don't need to believe common sense. Okay? Once well before the common sense, everyone in this world believes the earth is flat. Everyone, right? That's common sense, but it's wrong. You don't have to believe that. Okay, so mean squared estimator is just trying to say, evaluate what estimator is good or bad based on a cost function. It's similar to our least square problem, right? In least square, let's say in least square, we have yi theta I. Sorry, no y. So we have, let's directly work on this example. So let's say I have this x and y are jointly distributed with this. I can do samples, right? I do some example, I see some realizations. So this is x1, y1, x2, y2, dot, 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 right? So these are distributed. So how do I evaluate whether estimator is correct or not, or good or bad? It's just the weighted sum, the sum, this is expectation, right? Expectation is nothing but the values this thing takes multiplied by the likelihood that value occurs. So that will be like, I will evaluate the first one, I minus xi squared times probability of xi and yi. If I write it more clean, is x equal to small xi, y equal to yi, okay? So x may take multiple values. X and y jointly distributed. They take multiple values. And each of them occur with this probability. And for each of these cases, you will have an error. A sum over this error will give you a so-called least squared error. But this is in the expectation sense, so it's called a mean squared error. Any questions? Does this, this is our cost criteria. Can you define your own cost criteria? Yes. You can say this is a cube. You can say this is, I like this fourth. I like exponential, I like a log. Either way is fine, but this is most people agree upon. And this is so-called minimum mean square error. Let's work on an example. Oh, that's Yuntian, that's your estimator, okay? Let's see this estimator. Other example. Suppose I have y, are jointly distributed according to this table. Do you understand this table now? So x1, x can be 2 or 3, y can be 1, 2, and each combination occurs with certain probability here described in the table. Okay, so now I'm going to ask you, what's the minimum, what's the mean squared error of this estimator defined like this? Is this a deterministic function? This function is nothing, but if you tell me why, I will just multiply by 2, right? It's a deterministic function. If you send me the same y, I will give you the same output. That means deterministic, okay? All right, so how do you compute this? Let's plug in to the definition. So this is phi of y minus x squared. I need to make sure on average this error is small, right? We have to be able to compute the average. What is it? How do you compute this? Expectation is nothing but the summation over all the possible cases, right? The weighted sum of the value it takes. So for each pair of x and y, let's say if x equal to 1, y equal to 1, x equal to 2. Okay, that will be my phi of 1 minus 2. Is that right? Yes. And the squared times the probability in this case occurs. What's the probability? 0.4. Okay, and the other one is phi of y equal to 1 minus 3 squared times 0.1 plus phi of 2 minus, let's say 2 squared times 0.2 plus phi of 2 minus 3 squared times 0.3. On average, that will be the squared error for us, is the mean squared error. Or we can compute this number, by the way, very easily. This guy, phi of 1 is 2. 2 minus 2 is 0. This is exactly, right? So your estimator in this case is perfect. But only perfect for one case doesn't mean anything, right? You have to make sure you cover the other cases. What about this? This is a 0.1. Yes, right? This guy is 0.8. 0.2 minus times 4, right? This guy is 0.3. Overall, I have 1.2. That's the mean squared error. Is this good? I don't know. Compared to what others? So then you should ask, okay, if this simply multiplied by 2 may not be the best, what would be the best? The best will be given by a function that minimizes this mean squared error, right? So I can tell you we have a almost analytical formula for the estimator. The best mean squared estimator, so it's the one that minimizes this mean squared error. It's given by the conditional expectation. Let me repeat. The best minimum or the minimum mean squared error estimator is given by the conditional expectation. Okay, so Yuntian, I will ask you, so how do you how do you explain this formula? What is this term? When capital Y is small y. Okay, yeah. Let me be more, okay. So when y is y, x given y equal to y, what does this symbol mean? this is when capital Y is small y, x is still random. Okay? When I know Shenzhen temperature is 26, Guangzhou's temperature is still random. And its distribution is given by another, it's distributed. Okay? I can compute this conditional density or conditional probability mass function. And then using this, I can compute the expectation of x given y equal to y. Right? This will be a number, but that number depends on whatever you fit in for the conditions y. So if I gave you 26, you tell me it's 25.5. If I give you 27, this guy will change as well. So this guy depends on the realization of the random variable y. Okay, and the key property is that the minimum mean square error is nothing but conditional expectation. Okay, let's look at this case again. Let's see whether the conditional expectation will give us the best estimate. All right. So first of all, I know now by result in next slide. Okay, by result in next slide. We know function of y, which is defined as conditional expectation of x given y equal to small y, is optimal. What optimal in the mean squared sense? Okay, so let's compute this. What is this? Let's check. Phi of y is expectation of x given y equal to small y. Okay. I'm going to, the quiz will be about this as well, right? Today. How to compute this? Y is discrete, right? So y, I just enumerate the cases. Y can be 1, 2. Let's say if y is 1, then this is what? Expectation of x given y equal to 1 equals. So when y is 1, x is still random. Let's just repeat with me, okay? When x is y is 1, x is still random. It takes value 2 and 3. It takes value 2 with probability of what? 0.4 divided by the whole thing, right? So it's relative weight of this in the entire row. Okay, so this is 0.8 plus 3 times 0.2. Okay, so that will be 2.2. And if y is 2, then we get x given y equal to 2, which is when y is 2, x still random. It takes values 2 and 3 with probability 2 times 0.4 and 3 times 0.6, which is 2.6. Are we done? No, we only find a function. Is this a function? What is a function? Function is a mapping from argument to a value, right? So is this a function? Yes. You tell me a y, I can tell you what its value is. If y is 1, then tell you 2.2. If y is 2, I'll tell you the best estimate is 2.6. Let's see. So our best estimate, so minimum mean squared estimate, is a function of y. And this y is not, you don't have a formula, okay? Well, you do have a formula, you don't have a, it's not continuous. It's not like a 2x or something like that. It's divided by cases, right? So this is 2.2 if y is 1 and 2.6 if y is 2. Y can only take these two values, right? Now I can compute the minimum mean square error. So I would say expectation of this minimum mean square error of y minus x squared. We know how to compute this now, do we? But it take so how many cases? Sorry, these are now I need to plug in the capital Y, because I don't know what Y I'm going to see in reality, right? You can take with multiple values. So let's divide this case. Let me use another color. So in this case, when Y is 1, let's say, first of all, let's pick Y equal to 1. Y equal to 1, I always guess 2.2, right? So it will be 2.2 minus the cases for x, right? X equal to 2, then there's 2 squared times the probability of this pair occurs, 0.4, plus y equal to 1, I still guess 2.2 minus 3 squared times 0.1, plus, if I say now y equal to 2, then I always guess the estimate is 2.6 minus, first one is 2 squared times 0.2 plus 2.6 minus 3 squared times 0.3. This number would be, sum them together. If you believe me, I don't typically. I got 0.2. Okay, this is 0.2. Yuntian's estimator is 1.2. No, not his. Okay, so there's a previous one. This guy is 1.2. This guy is 0.2. Can you make it smaller? If the theorem is correct, then it won't be. And I can tell you the theorem is correct. Okay, so this is the best you can hope for. So how to design the best estimator? Conditional expectation. If you know that, you know almost everything about estimation theory. Well, there's other ways. There's a Bayes filters, there's particle filters, there's Kalman filters, there's extended Kalman filters, ensemble Kalman filters, uncensored. So there's so many different things, right? All of them are based upon conditional density. Some of them take expectations, some just take the maximum likelihood. The key is to find conditional density or conditional distribution. Okay, I think we have enough, all right? So I wouldn't prove this, and I tapped it. I typically prove them, right? It's pretty easy to prove. The steps are easy to follow, but it's conceptually hard. So every step, you may have question mark in your mind why we can do this. It seems 90% correct, but they just don't 100% get it. That's the way I think many of you will experience as you read through the proofs. And I think, but after we go over this again, as you review before the final exam, you check them again, your understanding will be different. Okay. Now, let me summarize. Now you finish almost the entire estimation theory, especially the part related to Kalman filter. So minimum mean squared estimate is just conditional expectation or conditional mean. That's the first one you should remember. Okay, I can ask you to repeat. The minimum mean square estimate is conditional expectation. As simple as this sentence, okay? And to continue, but the question is that, oh, well, did we solve everything yet? We have to be able to compute the conditional expectation, right? How do we compute? By definition again? The most general way is directly to compute the conditional mean is by definition, of course. Let's say by definition, well, we can know conditional density for sure. So expectation of y given capital Y equal to small y. We just need to compute this now, all right? If you think about estimation, all it boils down to is just the computation of conditional expectation. So by definition, this will be x, fx given y, and dx. Okay, I will say most estimation problem is trying to do this. Okay, that include particle filters, things like that, right? And but this is very hard to compute in high dimensional space, okay? In high dimension. Okay, when x and y are jointly distributed and there are 10 dimensions or 100 dimensions, multi-dimensional integral is really hard to compute, even numerically. So essentially, Kalman filter is nothing but trying to find a clever way to compute this. You first need to understand what he's trying to prove or trying to compute. There's some part is conceptually the result, and some part is a technique, right? There's some tricks. So the essential part for Kalman filter is just they're trying to find a smart way to compute this. Okay, let's take a break, and we will resume next. Okay, let's continue our lecture. I think during the break, some people asked me what exactly Kalman filter really is, how to connect to real-world examples. So far, we are only dealing with probabilities. So the way we're doing this now is we're trying to lay down the foundation first, really solid. Then we give you plenty of examples. In product 3, you're going to use Kalman filter to estimate the robot I think pose or location. And so typically Kalman filter is very popular is because of robotics and autonomy. I think that's one of the main reasons recently, especially autonomous vehicles. So we are talking about estimate X. What typically X is like your position, location, or even orientation of your vehicle. And the measurement could be your GPS measurement. And also your measurement could be your onboard IMU measurement. And those are all giving you information about where you are and how fast you're traveling. Those are your state, but those has noise, okay? You should cleverly combine those measurements to have an accurate estimate of your car's position. And if you really do autonomous driving level 4, level 5, you need to know, you have a high definition of maps, like a SLAM, and you have somehow additional measurement, like a locally align your point cloud with your map point cloud that give you other corrections. So you fuse all of this measurement information, those are all your Y. Okay, your Y is something like a point cloud that's taking in, and a GPS signal, and IMU measurement. And your X is the hidden variable that you're trying to estimate, is your exact location. It may possibly involve your orientation. And their speed. Their velocity is also sometimes state. Okay, so you're using those information to estimate the position or orientation and their velocities. That's one typical use of Kalman filter. Okay, you don't have to, nowadays you don't have to use Kalman filter, but Kalman filter definitely give you a starting point to understand those things. Okay, let's go back. I think we'll give you examples later on, but for now, I want you to truly understand the foundations, the math, and the fundamental nature. Fundamentally, Kalman filter or the minimum mean square estimate is just trying to compute conditional expectation. As I mentioned before the end of the last lecture, it's very hard to compute. I'm not sure whether you can. You have done this before now. If I ask you to integrate a function in 10-dimensional space, if you don't have a closed form solution, it'll be really hard. How do you integrate some function, very complicated function? You typically grading the space into small cubes or cells. It's like a finite element method, right? So you somehow divide into this, and assuming within this of this, the function value doesn't change that much, then you sum over them. It's like, but as the dimension grows, those number of cubes becomes larger and larger. It grows exponentially with the dimension. So once you reach 5 or 6, it's really hard. It's extremely hard. It's almost impossible. And but there's a catch. There's one exception, which is Gaussian. Okay, that's why Gaussian random vector is so important. If x and y are jointly Gaussian random vectors, Gaussian is not a variable now, it's a vector, okay? They could be, this could be Rn, this could be Rm. Okay, if they're jointly Gaussian random vectors, I'm going to define what they are, what joint Gaussian means. Then there is a simple analytical form for the conditional expectation. So you don't need to go over this integration. They have a closed form solution. That's the exception. That's why Kalman filter or why Gaussian vectors are so important for estimation or learning problems. Okay, as Yuntian said, in machine learning, the first part of few lectures all about Gaussian vectors, random vectors. So now let's give a review of Gaussian or normal distribution. You have learned normal distribution for sure, okay? The density function looks like this. Can anyone explain why this is called Gaussian? What's special about this? Okay, that's the least part. Okay, good. Central limit theorem tells me that summation of a large number of independent random variables eventually distributed according to Gaussian. Okay, but that's a property of Gaussian.
Maybe Gaussian discovery has something with the least square problem that if the error is distributed partially, the least square will give the solution.
Yeah. Well, there's a lot of story behind the definition of Gaussian random variables or densities. I want to tell you is that there's nothing special about this, okay? And you can have your whatever Shu-Yuan's distribution. I can say not exponential, I can say this is 10 raised to the power of this. Of course, you need to rescale it so that integrate, but the density function you have to integrate it to 1, right? So you have to make sure the constant is right. But that can be called Shu-Yuan's distribution. It's whatever it is, it's just something artificially imposed. Okay, I don't think in real world there's any kind of real distribution are exactly Gaussian. The reason this form is useful is due to many reasons. But one of the reasons is that it's very kind of good for us to compute conditional expectations. Okay, and of course the main reason is because of central limit theorem. So let's review. So these are few normal distribution in R1. My question is that suppose this is normal of mu1 and sigma 1. This guy is normal of mu2, sigma 2. Mu1 and mu2 seem to be both 0. I want to ask you which sigma is bigger? Sigma 2 is bigger than sigma 1, right? The variance is larger, so it's more, the density is more diffused. Okay, and how do I know? I can say, okay, I will say, I can give you a random variable. I ask you whether it's Gaussian or not. How do you check?
What do I know about the random?
You can, well, what do you need to know in order to prove or check it is Gaussian?
Technically, I think I need to know all the results.
You just need to know anything, okay? Any random variable, all you need to know is the density function or the PMS. If you want to prove one variable is Gaussian, you have to show its density function or PDF have exactly this form. It could be having different mu and sigma, but it has to be written as this form. Are you with me? If I like a Suyuan's distribution, then that's fine. You need to check whether it's of this form. It could be, right? So that's 1D, and you need to make sure that this guy integrate should be 1. Okay, so that's where this weird form of constant come from, right? You need to make sure this is a constant, right? You need to make sure the constant times this integrate out to 1. Then I'm not sure how many of you have seen n-dimensional Gaussian random vector. It's same. It has a mean or expectation, but also have a covariance matrix now. Okay, so in 2D, it looks like this. That's 2-dimensional Gaussian distribution. So exactly have this form. You can define your own form, okay? But everyone agree this form somehow it has a lot of nice properties, so we somehow use it as much as we can to represent practical distributions. The first of all is that this is also exponential. This guy, this is the covariance matrix of the Gaussian random vector, and this guy is almost like what? It's almost like X transpose times a matrix P times X, right? It's a quadratic form that we reviewed, at least in my online video lecture, there's review on those quadratic forms. And if you look at this, so this quadratic form is this number, okay? If you look at this level set, or let's say less than 1, for example, this will be the ellipsoid. It's an ellipsoid, okay? This is the ellipsoid. That's why if you cut this, and the level set will be ellipsoid. So you also need to multiply by this kind of a weird-looking formula. This is a determinant of the covariance matrix, and why we have this constant is we need to make sure the integration of this density function over the entire Rn is 1. That makes the density function a valid density function, okay? So if n is 1, then this becomes this formula. So if I want to check, you just need to know this form, okay? If I want to say whether a vector is Gaussian or not, you just need to check whether its density is of this form or not. In practice, it's very few of them has this form, but if you assume some random variable of this form, then you can create many of Gaussian variables that also have this form. Again, so there's nothing mysterious about those density formulas. You can define your own formulas. Okay, but let's stick to this Gaussian. If you want to check something is Gaussian 1D or ND, you just need to check the density function. Okay, all right. There are a few properties, as I mentioned, are very important or special about the Gaussian random vectors. And first of all, it's very simple to represent. If I say, suppose your distribution of your grades in the midterm, maybe it's we have a lot of full marks, right? Anyway, let's not talk about our grade. So typically, you think your grade may be something like this distribution, all right? But in reality, oftentimes it's like that, okay? Some good students are really good, and there's somehow 2 peaks, okay? And if you want to represent those distribution, in 1D it's easy, right? You just use somehow like a histogram, right? Its value, you can represent this curve very easily. But in high dimension, if you want to represent this very weirdly looking function, it's very hard, right? You need to have a big table to store all their values if there is no analytical form. But for Gaussian, it's very simple. The form is simple. It's only represented or characterized by mean and covariance matrix. Let me repeat. If I say something is Gaussian, all you need to know is the mean and the covariance. This is the vector, this is the matrix. If I know these 2 things, then I know exactly the density. In other words, the density are characterized by 2 parameters. One is the mean, the other one is covariance. Okay, so we don't need to store the entire values of this multidimensional function. Okay, I have an analytical form of the function that are parameterized by mean vector and the covariance matrix. The second fact, the first fact, this is a property. The first fact is uncorrelated joint Gaussian vectors are independent. What does uncorrelated mean? So it means covariance x and y is 0. They're uncorrelated, so the covariance is 0. Typically, it doesn't mean they're random, independent. But in Gaussian, that means what? X are independent of y. What does this mean? Fx, y, the joint distribution equals the marginal multiplied by each other. Okay, uncorrelation means independence. That's a special case, property for Gaussian. Can you prove this, Shuyan? How do you prove it? You're asking me or you're answering me the question? By definition, of course, you just need to check. It's very simple to prove. I want you to make sure it is simple to prove. Do you feel that or not?
No,
if I write it down, it take another 10 minutes. I think everyone will agree. This is very simple to prove. But it's, well, let's say conceptually simple, but it's tedious. Okay, you need to do a lot of algebra and to factor things out. But that's fine, it's conceptually simple. You just need, how do we prove this? You just assume their covariance is 0, then you check its density, and you find it out, oh, the density can be written as 2 marginal multiplied together. That's it, that's the proof. And you can go over these steps, you find it out. I don't need you to prove, but at least I need you to know what it takes to get its proof done. Okay. The second one is even more important for Kalman filtering. Is linear transformation of Gaussian is Gaussian. So if I say x is Gaussian, there's a mu x sigma x. Okay. Then I will say there's another number. Let's say 2 of x plus b is a linear transformation of x, right? 2x plus 3, let's say that. In scalar case. then I can conclude G is also Gaussian. How to prove this? Shuyan. How to prove this by definition? How to check G is Gaussian or not? Density function, then you do matching to see whether it is satisfy the form of Gaussian. If this is Gaussian, that's our assumption, you can compute the density of G, and then you will realize, oh, it is still Gaussian, because the density is of Gaussian form, maybe with a different mean and covariance. It has different parameter, but it's same form of the Gaussian variables, okay? If you want to check, you have to find the density function. But this is conclusion, whatever linear transformation you have, the result is also a Gaussian. The third one, I will do 10,000 emphasize all those. It is conditional Gaussian is Gaussian. That's exactly the Kalman filter based upon, okay? That's the fact, Kalman filter based upon. Conditional Gaussian is Gaussian. I'm not sure how much you can understand that. We will check this. Okay, we'll cover this part in detail, hopefully today. All right, let's go over a little bit depth, go into the depth of each of these facts. First of all, fact 1. So let's say X and Y are jointly Gaussian. I need to formally define this term for you. If you so joint, let me say jointly Gaussian, I will say by definition means what? Means X, Y as a whole vector. Let's say as a whole vector, is a multidimensional Gaussian. It's Gaussian. If I put them together as a bigger vector, this vector is a Gaussian random vector. Okay. In other words, suppose X is Rm, this is in Rn plus m, right? X is Rn, Y is Rm. That means X and Y jointly distributed as a Gaussian with some mean vector and some covariance matrix. Okay, so if these two are jointly Gaussian, then I can say these two independent or not. You only need to check this one of the facts. Okay, covariance equal to 0. Okay, covariance 0 if and only if it is independent. X and Y are independent if and only if their covariance is 0 for Gaussian only. However, this is something I think it's optional for maybe advanced student. I may upload some notes to explain. It could be possible X and Y are both Gaussians, but they are not jointly Gaussian. Let me repeat. If X and Y could be, each of them are low-dimensional Gaussians, but if you put them together as a vector, it's not Gaussian anymore. It's very possible. I will give an example, maybe upload a note to this. This will take some effort to explain. So the question is, another fact, this is fact 1.1, is if X and Y are both Gaussian, and X are independent of Y, then X and Y are jointly Gaussian. Both Gaussian means each of them are Gaussian. If you put them together as a vector, you have to specify the joint distribution. Okay, given the margin nodes, only given the margin node doesn't fully specify the joint. I hope that you can somehow understand that. Given two random vectors, the complete information you need is the joint distribution, right? But if I only give you two margin nodes, you don't know the joint. Okay, you cannot fully know the joint. Okay. So it's possible each of these margin nodes are Gaussians. If you put them together, there's cases that it's not a Gaussian vector anymore. But if these two are independent, the construction is Gaussian. All right, this fact somehow is useful, but I don't need you to fully kind of understand this. All right. All you need to know is that if X and Y are jointly Gaussian, then independence means covariance is 0 or uncorrelated. The second one is affine transformation of Gaussian is still Gaussian. So let's say X and Y. Oh, do I have Y? No. All right. X is Gaussian. This is a matrix. And these are deterministic matrix. This is deterministic. Then I define another variable, and this variable is a affine transformation. Do you know what affine is? 仿射, okay. So if I don't have this B, then that's linear. Okay, if I have this B, in the more rigorous way, we call it affine, but you can also loosely call it a linear as well. Okay, it's a linear function or affine function of X. If I can define this way, then Z is also Gaussian, which means this is mu of Z, right? It's A times mu times B plus B, and this is mu of Z. This is the covariance of Z. Actually, you can derive this right away, right? Because mu of Z is expectation of AX plus B. And we know the property of expectation as expectation times A times mu plus B. So that's mu of Z, right? And the covariance of Z is what? Covariance of Z with itself. AX plus B, AX plus B. But you know this plus B doesn't make any contribution. That's our property of covariance, right? That become A sigma A transpose. As long as I know, but this doesn't tell me anything about the distribution, the PDF of Z. It only tell me the mean covariance. The fact is that this Z I know will always be Gaussian. That's a fact. If you want to check that, you need to find the density function of Z, and you will realize it will be a Gaussian. Okay. This can be used to test whether a random variable is Gaussian or not. So now I'm going to ask you, Suyuan. This example, I have a R3 random vector. I call it Gaussian. Then I'm asking you, this is jointly Gaussian, right? X1, X3, X2, X3 is jointly Gaussian. Because I put them together, it is a Gaussian random vector. Now I'm going to ask you, is X2 a Gaussian? By definition, I didn't ask you to prove, okay? But by definition, if I want to know whether this is Gaussian or not, what I need to do? I need to find the margin nodes for X2. Okay, I have the joint, so I know the margin nodes. Or I know how to compute the margin nodes, right? So will be I need to integrate out X1 and X3 for the joint. Okay, X1, X2, X3, and DX1 and DX3. That will give me my margin nodes for X2. If I was able to somehow good enough in calculus to find it out, which I don't, I cannot. I don't know, I forgot quite a bit about those formulas for multi-calculus, multivariable calculus. But conceptually, you can do this, okay? By plugging in the joint density for this x vector, and you will find out this will be a Gaussian or not, okay? But we don't do this, right? Can you tell me a shortcut by the fact we introduce here, this is Gaussian or not, x2? So I will say x2 is equal to 0, 1, 0 times x1, x2, x3 plus 0, okay? Can I write this, okay? Your linear algebra should be good enough for you to see it right away. Is that right? So it is a linear or affine this is linear, linear function of x. And x is Gaussian, so x2 is Gaussian. So I don't need to do the integration. Okay, I can use the fact too to directly claim, okay, this is, I would say this is a affine transformation of x. So Gaussian. We're done, all right? So that's Gaussian. Now you see the fact. Is this a Gaussian? Shuyan, you're laughing. Is this Gaussian? Why? A3. Okay, so this is a affine transformation again. It's Gaussian. Are you with me? Can you check by definition? Yes, you can do integration. Now what I'm asking is this Y Gaussian? Y, can you write down a linear transformation to define Y in terms of X? What is it? 1, 0, 0, 0, 0, 1 times X. Okay? So you see this is also Gaussian. So the third one question that I ask you is x2 independent of x1? Is x2 independent of x1? Where's the covariance? I need to check. Basically, I can only, well, for Gaussian, I only need to check this guy, right? What is it? x2, x1 is the second row, first column. It's 0. So covariance is 0. So x2 independent of x1. Covariance 0 implies independence, but only for jointly Gaussian. Okay, what about x1 and x3? Covariance of x1 with x3 is -1. So it's -1. No, it's not. Sorry, not independent. Okay, not independent. Any questions? So we are trying to use those facts. Okay, here we come to the most challenging part and the most important part for Gaussian random vectors, which is the third fact. Conditional Gaussian is Gaussian. Okay, the fact formally states like the following: conditional Gaussian is Gaussian. That's the short notation or short summary of the fact. Precisely what I mean is that let x and y be jointly Gaussian. What does jointly Gaussian mean again? I put them together. It's a joint Gaussian random vector in Rn plus m. Okay, and I can partition their covariance matrix in this form. I'm not sure whether you can see that or not. I can give you examples. Suppose I have Z1, Z2, Z3. That's these are a random vector, okay? This may have the meaning of Shenzhen temperature. This is Guangzhou, okay? This is Beijing. Okay? I can partition in any way I want. Okay? I can say this is my x, this is my y, that's fine, right? I can define this in different dimensions. Then in this case, x is R2, y is R1. And they could be jointly Gaussian. You see what I mean? They can jointly Gaussian. So the conclusion is that the conditional distribution of x given y is Gaussian. Although I have explained this many times, I want to write it down again so that you can think, not only memorizing the formulas. So x, y are jointly Gaussian. Okay, so we'll have a density function, right? It's jointly Gaussian means this density function has the Gaussian form. Okay, right? So now I will say, what do I mean by conditional Gaussian is Gaussian? So Gaussian, given, let's say given y, capital Y equal to y, maybe Beijing temperature equal to 0 degree, given that fact, x is still random. Are you with me? X is still random. Given Beijing is 0 degree, doesn't fully specify what Shenzhen and Guangzhou really is. Okay, x is still random. Its distribution, its density will be what? X given y, x given y, capital X, small x given small y. Okay, so this capital Y equal to small y, that means Beijing equal to 0 degree. X is still random. I can find the conditional density. Any random variable have a density, right? It's still uncertain. I know this density is this, and we can show this density is a Gaussian. That's all it means. These three vectors, these three variables, when I specify z equal to a fixed number, I can find the conditional density of x given y. And that density function, it turned out to be also in a Gaussian form. That's what I mean by conditional Gaussian is Gaussian. if you check anything is Gaussian or not, you just need to check its density function, whether it is in the form of Gaussian or not. Okay, I hope that's fine, right? So then this become a few formulas, and which you can derive by hand, or you just somehow remember them. These are the few formulas that I remember in my life. So whenever you ask me, I know those formulas. I think we are open note exams for the final, right? So you don't have to memorize anything, but but these are so important that somehow I got memorized. I remember them whenever you ask me. Okay, so you can compute this density. It turns out this density of Gaussian form. Gaussian form is characterized by two parameters. One is mean, the other one is covariance. Okay, and we have a formula of this conditional mean and conditional covariance in relation to the previous marginal mean and the joint covariance. Okay, so the form, it looks like follows. I just want to give you how I understand this form. For example, this mu of x is expectation of x. Okay, and this is expectation of y. Okay, this is given, that means a realization of y. Given capital Y equal to small y, right? Those are covariance matrices. So, but it makes sense or not to you, I'm not sure. It makes perfect sense to me. I don't want to read this, but I want to explain this to you. When I know, always think about Guangzhou and Shenzhen, okay? In this class, we're in the Bay Area here, okay? So this is what on average you expect to see y. Maybe the average temperature of Guangzhou is 25, okay? Today you find out Guangzhou is 30. And this term will be a surprise term. This is what I call a surprise. If it is 0, no surprise. Today's temperature is the same as the average. If it is 30, this is 25 on average, then there's a 5 degrees surprise. Okay, today is hotter than I expect. How does y surprise on y got translate to your belief about x? So I know x typically about this, right? That's on average. Today I know Guangzhou is above its average. If we are positive correlated, that means I will somehow have a surprise effect got added up to the expectation of x as well, okay? Now this term, inverse of y, is typically, I would say this is how noisy y measurement is. Measurement is, okay? How noisy. The larger covariance, the more noisy, the less weight you want to put on the measurement. You see what I mean? It's too noisy. So sometimes give you 30, sometimes give you 0. So you wouldn't trust that much, okay? You somehow divide it. And this guy is the correlation between x and y. So how much y above the mean will got translated to x above its mean. Okay, so typically, so this formula is, I think you need to somehow have a sense what it is, right? Expectation times covariance x, y, and divided by noisiness, and times the surprise term. And this is the covariance minus cy. This we use less, okay? At least this part is to have understanding. So if you derive them by doing this, this is what? the joint divided by marginal, right? You can compute this. If you compute, you find out this Gaussian and its mean is covariance like this. So you can compute this, all right? I encourage you to do this. I think it will take a day or two for you. If for vector-wise. If for two random variables, I think maybe you have done this in your introductory probability class. I think so. You should. Okay. Now let's accept this fact. Let's do some exercise. At least do some. Now suppose x and y, x is R2, y is R, and z is jointly Gaussian. So I want you to say, can you compute the minimum mean square estimate given capital Y equal to, let's do something different. Let's this, y is 2. Okay, the reason is that makes things fun. So this is my x part, this is my y part, okay? I divide into these two parts. Okay, so I want you to say, what if I observe these two values of y, what's the best estimate of x given y equal to this? Now become estimation theory. The result we learned so far is that, okay, the minimum mean square estimate, this is our small y, right? Mean square estimate is conditional expectation. Okay, so first of all, I know x and y jointly Gaussian. Do we? We know z is Gaussian, so they together is jointly Gaussian, right? Sorry, I shouldn't write this. I should write more x and y, this pair is jointly Gaussian because I put them at the vector is Gaussian. So I know by fact -2 is Gaussian. That's the most confusing part for many people. You just need to see it more times, then you get used to it. And you should follow my suggestion. You always read or explain to yourself, when y is this, x is still random. That randomness has a density. That density somehow is Gaussian. Does it make sense? I think it should be, okay? I'm repeating this many times. I think somehow it's necessary for many people. And then I will know that conditional mean is what I want to do this, will be unconditional mean plus correlation, covariance, x and y, and times how noisy that is, times the surprise term. Okay? That formula somehow you got. And I can tell you this guy, the mean is what? Unconditional mean is 1. This x, this is 1, right? Plus covariance of xy, what is it? Covariance of xy. Covariance of x is z1, right? Y is z2, z3. So it's 1 by 2. 1 by 2. So it's a covariance of z1, z2, which is 1, 2 is 1, right? And z1, z3 is 0. That's my covariance of xy. You should be able to read this table or this matrix, extract any information you need. And times sigma y inverse. What is sigma y? It's a 2 by 2 matrix, is this part. This is my covariance of y with y. This part, right? So that will be 4118 inverse times y is the surprise term, 2, minus the mean, which is 2 and 3. Are you with me? Okay, so it's 1 plus, I would say this is my favorite word, some number, okay? You can compute. It doesn't add any value or knowledge to you if I calculate this for you, right? You can compute the inverse. That will be some number. That number means the conditional mean, also means the minimum mean squared estimate of x given y. I think we're about time. So, but I want to point out, you can also find it out by conditional density. Conditional density. Sorry. let me restate this sentence. I can also find, we can find the exact conditional density of x given y, small x given small y. Because this will be what? 1 divided by square root of square root this, e to the something, right? Divided by x minus mu divided by sigma squared. Because this some number a will be my mu here. Okay? And also need to find this, which is, you can also find by conditional of this y equal to small y, based on the formula we had on last slide, this guy. I think you know all of these numbers. And sorry, let me just finish this within 30 seconds. So that will be sigma x minus sigma xy, sigma y inverse, sigma yx, which is 2 minus 1, 0 times 4, 1, 1, 8 inverse times 1, 0. Okay, this is some number b. And this b will be this, with its sigma squared. Okay, so if I find this mu x given y, find sigma x given y, I know I can write down the density if you need, but typically don't. All right. Let's get started. I think I will assign another homework today. So without homework, I think it's hard for you to really or truly understand these abstract things. But I want to emphasize the probability is very useful, not only for control, it's actually for many other fields, including robotics and machine learning. So I think the thing we reviewed in this class for probability will be helpful for you to understand other class or even understand the literature. Will be very helpful for that as well. And so let's quickly recall what we have learned last week. I think we finally started deriving Kalman filter. But before deriving Kalman filter, we spent a lot of time reviewing probability, basic probability. And there's only a few things I want you to kind of remember. First of all, what does Kalman filter do? In terms of its functionality, it's nothing but try to estimate the system state given the system input and output data. Okay, that's the very first thing. It does the same thing as the Lundberg observer or any kind of observer, but it just takes a probabilistic or stochastic view of the system behavior. Okay, and I also told you that without any proof, I told you Kalman filter is nothing but compute conditional mean. All right, but we start to see why that's the case, because last week we finally reached to the fundamental theorem of estimation, which is what? What's the estimation problem, by the way? You want to use measurement from y, which you can measure, to estimate some hidden variable which you cannot directly measure, which is x, right? There's many ways you can do this estimation. And of course, some of them are good, some of them are bad. But if we agree upon a common criteria, which is called mean squared error, then the best estimator or estimate, or the so-called minimum mean squared estimate, is given by the conditional expectation. Okay, we show you why that's the case, and there's a proofs you can check. So whenever you want to estimate something based on other measurement, okay, if you want to just do the best minimum mean square estimate, simply you just need to compute the conditional expectation, right? That's why conditional expectation is so important, and that's why we spend a lot of time reviewing the concept of expectation and conditional expectation. And so Kalman filter is nothing but compute conditional expectation because we want the minimum mean square estimate of the state given the input-output data pairs, okay? As I mentioned last time, it's very hard, although conceptually or analytically, it's easy to write down the formula, conditional expectation, this one, right? But how to compute it is very hard if the dimension of the state and the input-output data are large, okay? So I don't think we can do that in general, but a very special case for which we have analytical form for conditional expectation is Gaussian. Okay, that's why Gaussian is very important. So we spent some time to discuss Gaussian random variables, Gaussian random vectors, okay? How to check whether a given random vector is Gaussian or not. Yeah, Shuyan. How to check whether a random vector is Gaussian or not? By definition. Okay? What's the definition of Gaussian random vector? It's PDF, probability density function of this form. Okay? Whenever you can write a PDF like this form, it's a Gaussian. If not, it's not. Right? As simple as that. Okay. But Gaussian random vector has so many nice properties you have to remember or you have to know. And there's three things that I want you to remember, at least, before the end of this class, at least. There's three facts. Okay, the reason I call them fact is that I don't prove that for you. I want you to somehow kind of believe me, all right? So typically I'm okay. I'm bad on calculating the numbers, but these conceptual things I'm okay, right? So believe me, fact one, uncorrelation or uncorrelated Gaussian means independent. But an independent also implies uncorrelation as well, right? But for Gaussian, you can go both directions. But for general random vectors, you can only go from the independent to uncorrelation, not the other way, all right? The second is very important thing is linear transformation of Gaussian are Gaussian. Okay, if I have a jointly Gaussian random vectors, or you just have a Gaussian random vector, then linear transformation of this random vector will be Gaussian. And we know how to compute the mean and the covariance for this linear transformed Gaussian, right? The third one I put a lot of kind of emphasize here is the conditional Gaussian is Gaussian. Okay, so how should we, let me see whether I have other ways to explain that. Yes, okay, no, where is it? Conditional Gaussian is here. Okay, conditional Gaussian is that I have x and y are jointly Gaussian. Jointly Gaussian means if we put them together as an overall random vector, that random vector is a Gaussian random vector. Okay, if that's the case, then x conditional on y taking some small y values is also a Gaussian. How should we understand this? Xiaohan, how should we understand this? given y equal to y, there's only a few kind of sentences I summarized for you. You need to memorize, okay? Not for English, just for the way you approach the problem. Given capital Y equal to small y, x is still random. It's not completely specified, right? And that randomness has a density. It turns out that density is a Gaussian. As Yuntian said, you just need to check the density, right? It turns out that density is also a Gaussian. So that's why conditional Gaussian is Gaussian. And the formula is given by these two things. Gaussian random vector is characterized by two parameters, okay? One is mean, the other one is variance or covariance matrix. Okay, if you talk about Gaussian random vector, we have a covariance matrix. Okay, each of them, if I gave you the y value fixed, then each of them have a formula. I explain what this formula means. Okay, so I think last time we finished this example, right? Let's do another one. All the Kalman filter, I'm doing this derivation now. It's just the key elements in deriving Kalman filter. Okay? If you understand those simple examples, we put them together, that become the full derivation and the whole story about Kalman filter. Okay, let's look at this example first. Suppose I have a z random variables. Okay, I say z is distributed according to a Gaussian. Shuyan, is this Gaussian? Yes, right. I told you it's Gaussian, right? What's the mean? What's the dimension of this Gaussian random vector? 3, right? This is Gaussian in R3, and this is the covariance matrix. Now I'm going to ask you one thing: how to read this matrix. What does this mean? This number 0.5 means covariance of Z2 with Z3. Okay? Each of this number is a covariance between certain components of the random vector. Okay? So you know everything about this random vector. Now I'm going to ask you, this is a random vector. Then I say, let's define that P, I define another random vector, okay? P is Z1, Z3, okay? Can I do this? Of course. I only pick the first and third element of this vector, and I call Q equal to Z2. Okay, so I want you to find expectation of P given Q. I say Q equal to 3. Oh, I want to find the conditional expectation, okay? So again, conditional expectation is the key for understanding Kalman filter. So to understand this, given Q is 3, P is still random, right? And I want to know that distribution of that randomness so that I can compute its expectation. Okay, so how do we do it? First of all, is P, Q jointly Gaussian? Why? So if joint Gaussian means I need to put PQ, that will be a Gaussian. Is this Gaussian? That's Z1, Z3, Z2 is this Gaussian. Why? It's a linear transformation of Z, right? So no matter how I arrange the coordinate, it will be Gaussian, right? So that will be 1, 0, 0, 0, 0, 1, 0, 1, 0 times Z. Okay, that's a Gaussian. Are we with me? Okay, if we're in the Gaussian world, everything is simple because conditional Gaussian, it's Gaussian. So I will say, if I write like this, P given Q equal to 3, this whole thing, if I write like this, how do you understand this thing? It's a random vector, or of course, we can call random vector, either way is fine. It's two-dimensional random vector. Because P, the thing matters is P, all right? P is two-dimensional. P is a two-dimensional random vector. Its distribution is specified by the original P given Q equal to 3. So Q given equal to 3, P is still random. That randomness is a Gaussian, and it's two-dimensional Gaussian. And by the formula, we know this two-dimensional Gaussian given Q equal to 3. What's its formula? Of course, by definition, but we have a formula now. You have to start. For Gaussian, we have a formula. So the mean is unconditioned mean, all right, plus covariance of PQ, covariance of Q inverse times surprise. What are the surprise? So we see 3, but we expect E of Q is what? Is 5. So on average, it's 5. But it surprised me a little bit. It only sees 3. It's below its expectation, all right? But then I need to normalize it by how noisy that observation is. Because the more noisy the less trust, it's less reliable that measurement is, right? So then that is how correlated these two things are. Then this thing will give you a correction, okay? So let's see. So overall, I think it's just plug in the formula. EP, what is the EP? -1 to 4, okay? What about covariance PQ? So covariance P and Q is covariance Z1 with Z2 and the covariance Z3 with Z2. Okay, it's 2 by 1. So in the exam or in whatever test, if the dimension is wrong, I think I would just give you almost 0. If the number are wrong, dimensions are right, you almost get the full mark. So of course you need to be, if there's involved some calculation, you make calculations wrong, that's fine. Okay, so this will be Z1, Z2, you know how to read this, right? This is -1, Z3, Z2. Z3, Z2 is a 0.5, okay? So this guy is -1, 0.5. Covariance Q is what? It's this guy. So it's 1 over 4. So we don't need to do an inverse matrix. It's just the inverse of a number and times in the -2. Okay? Overall, I will get, I think it's -½ and 15 divided by 4. So is that clear how to compute conditional expectation for Gaussians? If this is clear, you are 90% there towards fully understanding. Well, no, sorry. In terms of content, yes, it's almost 90%. But in terms of hardness, or the most challenging part, we haven't seen it yet. It's maybe still quite a lot, all right? We're going to fix that today. So this is the conditional expectation. Okay, I have another example. I think you now start getting almost bored by those kind of examples. I mean, I'm gradually somehow warm you up for the more intense derivations. So this one has more meaning, okay? I have X, a two-dimensional Gaussian random vector with mean this and the covariance that. I have Y defined as a matrix times X plus V. V is another noise. It's another Gaussian random vector. The thing that I have for you is I know V is independent of Y. Now I ask you to compute the minimum mean square estimate of x given y equal to 1 and 1. All right. First of all, what do we need to compute? The minimum mean square estimate of x given y equal to 1 and 1. What does it mean? So you see a observation y equal to 1 and 1, and you want to find the best guess for x. You don't know it, right? If you didn't take this class, the best guess for you would be, I will ignore the noise. I will invert this matrix. I can find x. Okay, that's one heuristic way to do it, right? And the way we are trying to do it is the optimal. Okay, it's the minimum mean squared error of x given y. So, what's by fundamental theorem? We know the minimum mean square estimate of x given y equal to 1 and 1 should be, what is it? Conditional expectation, all right? Although I didn't ask you to directly compute the conditional expectation, I want you to find the best estimate. That's conditional expectation. So all we need to do to solve this estimation problem is to compute this conditional expectation. Now the second step is that, okay, how do we know how to compute this? First of all, you need to know the density of x given y, right? It's typically hard, but in this case, we will try whether they are Gaussian or not. Okay, the first question I will ask you, y and x are jointly Gaussian? I'm asking you, okay, I'm not stating this fact. It's a question mark. Are they jointly Gaussian? The reasoning goes like the follows. Okay, typically I don't test this kind of reasoning, but I want to tell you the full story. So I know x is Gaussian, all right? I know v is Gaussian, okay? I know x independent of v, that's important, okay? If both of them are Gaussian, they may not be jointly Gaussian. I mentioned that last time, but I didn't prove it. I will give you a counter example in the Blackboard. Okay, I'll upload the counter example. I can create many counter examples. I just don't want to go through them in class. But if they are independent, then the claim I can make is x and v is jointly Gaussian. So the whole vector is Gaussian. Are you with me? The direct consequence of these three is I can only say x and v is jointly Gaussian. I cannot say other things, all right? But y is a linear transformation of x and v. So y is Gaussian. I can only say y is Gaussian. Now I will ask you whether y and x are jointly Gaussian or not. So what I really want is I want to see whether the whole vector is Gaussian or not. Are you with me? Yeah, it's still a linear transformation. Great. So it will be identity 0, x and v. This is A identity, right? I will call this guy A, all right? I'll call this 1014 A matrix. I'll call this guy A matrix. So I will say linear transformation of Gaussian is Gaussian. So x and v, y. So I'll call this Gaussian, which means x and y are jointly Gaussian. I think this kind of notation is incorrect or is not precise. So I will say x and y are jointly Gaussian. That means the whole vector is a Gaussian random vector. Okay. Now we are in the Gaussian world, then everything becomes simple, right? So I will say the minimum mean square estimate I'll call that hat of x. It's conditional expectation of x given y equal to 1 and 1. Now we plug in formula, right? The part you like the most is you have some formula to plug in and calculate some numbers. Without any thinking, you can get some marks, right? You can get some credits. So that will be expectation of x plus covariance of x with y times covariance of y inverse times surprise, 1, 1 minus expectation of y. Okay? Now I want to ask you how to compute those terms. So maybe I know EX, right? What is EX? Let's call it, let's say EX. What is EX? Oh, EX is given. EX is 4 and 4. Okay? Let's say 3.2. Now I want to compute, let's first compute covariance of x and y. Okay, this term. So how do we compute it? Let's write down by definition, right? So you plug in x, y is defined. I didn't tell you what y is. Y is defined indirectly through x and v, right? So that will be ax plus v. Okay, so then I can compute, right? By the properties of covariance, which is just the property of multiplication, okay? So I know this is the covariance of ax plus covariance of xv. Okay, and I know this is covariance of x with itself, A transpose, right? I move it. Okay, what about covariance of this? 0. Why? Okay, if x and v are independent, covariance has to be 0. That has nothing to do whether these two vectors are Gaussian or not. You see what I mean? I encourage you to prove this by yourself. It's super simple.
I actually proved it on in-house.
Oh, I already did this, right? Okay, so then I don't want you to do that again. Okay? Or at least you can prove it now, okay? Because the independence means the factorization of densities, then covariance becomes 0, okay? So, well, you can check our previous slides, maybe. I forgot we proved it before. Anyway, this is 0, all right? So overall, I will have, what is it? Covariance of x with x just means covariance x, right? That's this guy, okay? That's 4, 1, 1, 2. A transpose is 1, 1, 0, 4. Overall, I will have 5, 4, 3, 8. A transpose. I got it wrong. What is A? Okay. A transpose, sorry. 1, 1, 0, 4. Okay. So overall, I have, this is the 5. This is this is a 4, sorry. 4, 8, 1, 9. Is that 9? 9, okay. Good. I don't care. So anyway, so up to here, my job is done. After there, the calculator does it, or AI does it. The only thing you are better than AI is from here to here. After that, I think everyone is worse than the computer, okay? 3.3, one more thing is we need to compute covariance of y, because we need to do the inverse. So covariance of y is ax plus v, ax plus v, all right? So I will have covariance of ax with ax. That's almost like multiplying these two terms. Covariance of ax with v plus covariance of v with ax plus covariance of v with v. You should be very familiar with covariance properties. It's not really properties, it's a multiplication of these two sums. Because covariance is multiplication of the two terms, okay? So this guy is A covariance of x, A transpose, plus this is A times 0, okay? Plus this guy is 0 as well. Those zeros are matrix 0. All right, it's everything is 0. And is this guy 0? No. Why not? It's noise. Expectation is 0, covariance is not 0. Okay, otherwise it's not random variables anymore. So this is what's the covariance of V and V? Identity, right? So I told you. So that's 1, 0, 0, 1. So overall, I think I will have something that I don't care, right? You know, this guy. You should care, right? So during class, I don't need to care about those calculations. So overall, I should say you can check the MMSE based on this formula. Then I know everything, right? Do I know everything? Oh, I need to know expectation of y, right? So let's say expectation, that's 3.4 EY is very simple. It's A times EX plus EV. EV is 0. So A times EX, which is 4 and 20. I think that should be correct. 420. Okay, overall I have everything I need. So this will be something you can check. 44.1136. I don't believe my calculation, so that number doesn't have any. Anyway, I think you know how to compute, that's fine. That's how I can calculate it. I may be wrong, but just for your ref. All right, you got it. Now you know how to compute the minimum mean squared estimate of something. Some hidden variable given other measurable measurement data, okay? Any questions so far? Now we have everything. Let's go back to our key things, which is the Kalman filter. Let me define a few notations a little bit more carefully. I think you have seen this format many times so far, but we haven't explained in detail what are these means. Any questions? Huh? Gaussian? Oh, jointly Gaussian. I think this lecture we have it, right? Did we do it? Let me remind you, it's not, see that, okay? Jointly Gaussian, by definition, this is triangle means definition. This is as a whole vector, x, y is a Gaussian. So I can have two Gaussians, but Gaussian means the marginals. So these two marginals, fx, are Gaussian density, fy is Gaussian density. But that doesn't mean the joint is Gaussian. All right? Not unless, one special case is that if these two are independent, then the joint will be directly this multiplied together, that will be Gaussian. Okay, you can check that very easily. By the way, you just multiply these two, you find out this is a two-dimensional Gaussian with diagonal coercion matrix. All right. No, it's just we put them together as a whole vector is Gaussian. No, let's do this way, okay? This jointly Gaussian, by definition, means, by another definition, sorry, more explicit, this can go this way. It's just x, y, this is Gaussian. You see what I mean? This thing is a Gaussian, jointly Gaussian, right? This joint distribution is Gaussian distribution. That also means if I put them together as a whole vector, that whole vector is Gaussian. All right? Because in this class, the only thing that I ask you to somehow get yourself familiar with is that every of these things may be vector. All right? In your introductory random variable class, I think by default, everything is scalar. Here, by default, it's vector. So this could be three-dimensional. This could be two-dimensional, right? What I want is the five-dimensional thing is a Gaussian, all right? If these two are independent, you multiply them together, it will be Gaussian. You can check that. That'd be very simple to see, all right? Great. Any other questions, by the way? We should clarify those questions before we move on, right? All right, now let's talk about this Kalman filter setup. There's many variations of Kalman filter. Okay, there's extended Kalman filter. I think we will cover that as well, maybe next lecture. And there's the ensemble Kalman filter and scientific Kalman filter. There's so many different versions of Kalman filter. But the most fundamental one, the basic version is this, okay? So as I mentioned before, the system is still linear, but is the system linear or not? Depending on how we define linearity. So it's a linear or affine in state, affine in control, right? It just have some perturbations of the noise, which this guy is called process noise, and it's Gaussian. Okay, and this guy is called measurement noise. So the measurement is not clean, can have some noise, and you know some noise random distributions, which is also a Gaussian. Okay, it's zero mean, and it's also has a distribution. All right. My notation is similar. I think, let me see. I think typically I don't do this, right? I think this should be P dimension, right? This should be M dimension, right? That's the input dimension is M, state dimension is N, output dimension is P, okay? So now I'm going to ask you, what's the dimension of this covariance matrix? Or what's the dimension of this guy? This is the P, the same dimension as Y, right? So this is a P-dimensional Gaussian with zero mean and some covariance matrix. And the process noise is Rn, so it's n-dimensional Gaussian random vectors. All right, so it's just start, and also the initial distribution you also don't know exactly. Okay, you have a expected value mu 0, and you have some covariance matrix capital Phi of 0, right? The assumption is that the initial state is independent of all the process noise for all k. This means for all k. And x0 is also independent of the measurement noise, and the measurement noise and the process noise are also mutually independent for all k. Under these assumptions, I'm not sure how much you can get out of these assumptions. I would say here, A, B, C, D matrix. Here I say A, B, C, D matrix, C, K, D, K. I put this in the more general form because K can be dependent on, A, B, C, D matrix are deterministic, but they can depend on K. They can change over time. Okay, in this particular setup. Those are all deterministic. What deterministic mean again? Single value. I may not tell you those numbers, but you know eventually you will have some number there. It's not like a random, which has multiple values, and each of them has different kind of probability density or mass distribution. Okay, these are deterministic. Okay, let's do one step. I assume initial state is not completely known. Okay, it has distribution. If you know that for sure, then of course you can make this covariance very, very, very small. That's fine. Okay. So now I'm asking you, what about x1? X1 is Gaussian or not? I know x0 is Gaussian, right? According to my modeling assumption, is x1 Gaussian or not? Oh, by the way, there's another thing. UK is deterministic as well. Okay? UK is something you send to the input. You send to whatever input you have. Okay, so it's deterministic. Okay, so this guy is deterministic. That means this guy is a number. All right, and x0, so x1, so x1 is a1. A0, x0 plus B0, U0 plus W0 or omega 0. Okay, so this is Gaussian. This is a number. This is Gaussian as well, right? I have a summation of two Gaussians. Is this Gaussian? Only when omega 0 and x0 are independent, I know for sure it will be Gaussian, right? It's the same thing like what this example says, all right? This is two Gaussian summing together, but you need to assume they are jointly Gaussian before you can move on, right? That's why we have those assumptions. You know, mathematicians are really, really serious about everything they put on the paper. So all these assumptions has a meaning, you need those each of these to make sure everything is Gaussian. Okay, so X is Gaussian, omega 0 is Gaussian, x0 independent of omega 0. Overall, you will say x0 omega 0 is Gaussian. Okay, and then you know x1 is Gaussian because x1 is a linear combination of Gaussian, right? This Gaussian. Similarly, I can derive y1 or y0 is Gaussian. So overall, implications of these assumptions, I hope you can believe me, I also encourage you to go over them. Check x1, y1, x2, y2. Check a little bit, you will see what you need to guarantee everything is Gaussian. So Kalman filter essentially lives in the Gaussian world, okay? xk is Gaussian, yk is Gaussian for all k bigger or equal to 1, and everything is jointly Gaussian. I would say, let's assume, okay, everything I mean xk with yk, xk with yk minus 1, all of those things are, everything is jointly Gaussian. We don't need to check like this anymore, okay? That would take a lot of effort. Let's believe all the variables you see, they are jointly Gaussian, okay? If you don't feel comfortable, you can check a little bit by yourself. I think you'll have all the tools you need to check those things. All right, so another symbol that we introduce is the capital Y. Capital Y is the measurement history, okay? From Y0 up to YK. So capital YK is all the measurement you received, collected, up to time k. So this vector will grow bigger and bigger as time goes on. Okay. So we're in the Gaussian world. That's the modern assumption. What we're trying to do, remember what Kalman filter is trying to do? UK, YK, I want to find XK hat. That's what Kalman filter tries to do, all right? But we are living in the probabilistic world now, and we want to make sure what we estimate is the best according to mean squared error. So state estimation problem, or the problem we care about, is find the minimum mean square estimate of xk given capital YK. Of course, also given, that doesn't matter, also given all the u's, okay, u0 all the way to uk minus 1. All right, those are deterministic things. Those we don't need to given or not, but that's you know that, okay? So the solution, Zhu by fundamental theorem, the best estimate of xk given yk is what? Conditional expectation, right? Is this guy, all right? So all we need is that, okay? So Kalman filter, but compute this guy. You should have a high-level understanding of what they're trying to do. Then everything else is details, right? The devils are in the detail. The details are important, but the most important thing is know what we're doing. Otherwise, all the derivation make sense, but they don't just come together. They just fall apart, all right? So all we are trying to do is to compute conditional expectation. Okay, I somehow repeat this many times, but now you see more clearly about this statement. Well, let's prove how we can do this in a recursive way. It's very simple. There's one step that takes some effort to understand. All the other steps you already know. Okay, so let's introduce a few notations you often see from the literature. My notation may be a little bit different from some existing books or literature, but should be consistent with most. All right. Let me define some notations. All of these has derivation. So x hat in the context of Kalman filter is always means the best. So it's the minimum mean squared estimate. Okay. That hat. A hat means sometimes denote estimate, not the true value, right? But you can have very stupid estimate. So in this context, x hat always means the best estimate. Okay, the minimum mean square estimate. And here is the x hat of k given k means the best estimate of xk given measurement up to time k is this guy. All right, and xk hat k minus 1 is the best estimate of xk given yk minus 1. That's definition. Can I have this? Xk given k plus 2. By my notation, yes. Can I have this? Mathematically, yes. Practically, also yes. If you know the measurement up to, by definition, this means, I want you to make sure you can generalize my notation. This is k plus 2. That's what I mean, right? So that means the best estimate given measurement up to k plus 2, the best estimate of xk given measurement up to k plus 2. So you have somehow not only to time k, but you have two more measurement coming in before you make the estimate of xk. You could have that, especially you're not running things online, right? You collect a lot of data, you want to say, what's my best estimate of x10? But I have all the measurement up to y100, that's fine.
Is this better than x?
Yes, sure. You have more information, sure. Sometimes this is called smoothing. All right, so this is fine. But we don't use it. I just want to make sure you can generalize my notation. Some students struggle with my definition of here. I'm not sure how much you struggle. PKK, the covariance matrix of xk. So this is, let me say, this by definition, okay, this is a covariance of xk with xk given yk. Yuntian, can you kind of explain this now by reading this formula? What does this mean?
The undetermined matrix of our estimation as given all measurement up to time k.
Okay, so this guy is y0 all the way to yk, right? That's all the measurement I collect over time. If I see this measurement, you should follow my structure, okay? Or try to follow roughly. If I see this measurement, I still don't know xk for sure. So xk is still random. That randomness has a distribution, right? It's random. For any random variable, I can compute its covariance. Are you with me? For any random variable, I can compute its covariance. This is the covariance of that randomness. What randomness? So the xk given all the capital YK. Does this even make sense? Yes, it makes sense. So given YK, capital YK, your belief about xk changes. It's still random, but the randomness changes. It's like today's temperature of Guangzhou. I tell you, then your belief about today's temperature of Shenzhen will change accordingly. But the updated distribution is defined as xk distribution given yk, and the covariance associated with it is called covariance of xk with xk. All right, so that's this. And this guy is the same thing, given measurement up to k minus 1. Then my belief about xk changed. It's still random, and that randomness has a covariance or lead to a covariance. By definition is this. Okay, you should know low things by hat. Those are the numbers. Okay, you take expectation already. Those become numbers. It's almost the same like a x minus 0 or x minus 1, things like that. Right. The only thing matters is that x is still random, but the randomness is not the original randomness of x. It's the modified randomness after you see y. Okay, I think that takes some effort for you to understand. And I have simplified notation, which is if I don't have a bar given, that means given the time up, given all the measurement up to the current time, k. So the things I want to try to estimate, the time I want to estimate the state is the same as the time is same as the time step I receive all the measurement. Okay, so these are the same. If I say k minus k, then I need to specify. If these two indexes are different, I need to specify them. Otherwise, I will give pk for shorthand notation. Okay, now we have all the notations. I think we'll derive Kalman filter. All right, I think maybe we should be able to finish after next class. All right, take a break. Okay, let's continue. Before the full or formal derivation of Kalman filter, let's do one step. Okay, just see the flavor of the derivations. Okay, so all we need, let's not talk about general term. Let's just look at this example for which you have some number to, some people like to see some numbers, okay? This is a special system. First of all, we don't have U, right? There's no deterministic input. U doesn't change anything of the common filter, at least in a hard way, but it just it doesn't change. And also, we don't have measurement noise. The measurement is almost a deterministic function of state. Okay, so again, all the other setup are the same. So our initial state is a Gaussian, and the measurement noise is Gaussian, and this A and A matrix and the measurement noise are the same, has the identity covariance matrix, and this sigma x, what is it? Oh, this is the initial state distribution, initial state Gaussian covariance matrix, and C is 1 and 2. Okay, now I'm asking you to compute two things, x1 hat and x2 hat. Again, our notation says this is what? The best estimate of x1 or x0 given measurement up to y0. This is the best estimate of x1 given measurement up to y1. So these are already the common filter. Okay? Although you don't see that, it looks like another probability exercise, but it's indeed common filter already. Okay? It's different a little bit from previous example because I'm gradually adding more element, let you to see the flavor of the proof. Okay, first of all, let's do which one? Let's do the first one. Expectation of x0. Okay, so x0 hat is expectation of x0 given y0 equal to 1. Okay, how to compute this? X, Y are jointly Gaussian, right? So we need to find first, okay, that's 1.1. We need to find x0, y0 joint distribution. Do we have it? No, we don't. We know x0 is Gaussian, and we know y0 is defined in terms of x0. But I didn't tell you their joint. You need to tell me the joint first before we can move on. Okay, so we know these two, the distribution, but we know these two is jointly Gaussian, right? This is jointly Gaussian, which is have this mu. This is, I will call it EX0, EY0, right? And we'll have some covariance matrix that we need to compute, right? Do you know how this thing is constructed? This guy will be covariance of x0. This is the covariance of y0. This is the covariance of x0 with y0. This is covariance of y0 with x0. This is so small, this is 0, okay? There's no magic because I told you the x0 could be R3. In this case, it's R2, right? Could be R3, y0 could be R10. Either way is fine. The way we structure is just the way we partition this matrix. And this part will mean that. Okay? I think after a few examples, you will be feel more comfortable about this. So let's try to compute what we need for this joint distribution. For joint distribution, it's Gaussian, so we need to know its mean and covariance. This is the big covariance, right? Let's look at, let's see which one. So we know, let's do one by one, okay? We know EX0, it's given, right? It's 0. What's the dimension of X? Dimension of X is 2, right? So it's 0 and a 0. You have to make sure this vector dimension is right. No, hold on. X is 2-dimensional? Yes. Okay. And what about EY0? So it will be C will be 1 and 2 times 0, 0, which is 0, its number. The dimension has to be correct. That two things are simple to construct. Now let's look at what's the covariance of x0, which is sigma x, right? So this is 2, 1, 1, 1, which is the sigma x given in the statement of the problem. You with me? Oh, by the way, I see some students have. Why the structure of the covariance matrix like this? Shuyan, how to argue? How to prove? By definition, okay? Of course. Why not? You can see what's the covariance. You want to find the covariance of x0, y0 with itself. Okay, you partition it, you will find it out that's the case. Just imagine this is x1 and x2, x1 and x2. What about this? This will be x1 with x1, this is x1 with x2, right? x2 is the same thing, it's a block operation. Okay, I think that should be enough. Okay, let's look at covariance of x0 with y0. How to compute it? Will be covariance of x0, c times y0. So will be c times x0 will be c transpose here. Okay, so will be 2, 1, 1, 1 times 1, 2 c transpose, which is a column vector 4, 3. Right? Yes. Okay. Then I need to compute y0 with x0, which is the transpose of the previous one, which will be 4, 3. The only thing left is covariance of y. Covariance of y with itself, right? So that's what? It's a c times sigma x c transpose. I jump one step only, right? It's covariance of cx0 with cx0. So c will be moved out to the left and to the right. The one to the right has a transpose. Okay, so this will, I think it's 10. Okay, we have everything we need for this thing. So the joint distribution is specified. As long as we know it's jointly Gaussian, we can compute conditional expectation by our formula now, right? So our formula tells us x0 hat is expectation y01 is the unconditional mean, which is ex0, which is 0, 0. Let me write the formula, right? So ex0 times covariance x0 with y0, covariance of y0 inverse times surprise. How much surprise we got? Y is 1, right? So 1 minus the expectation of y, which is 0. So the surprise is 1. Okay, after plugging all of that, I think we can find it out. This is 0.4. This is 0.3. You can verify this number. The correctness of this number, I don't care, right? So you should care. We have one-step Kalman filter. Everyone can do one-step Kalman filter now. The initial step. You know, any kind of induction type of proof, the key is how to move from one step to the second step. After that, it's done, right? So let's see, the next part is the most challenging one, or the fun part. By the way, you will see later on we need to compute this P of 0. Okay, you will see, we know how to compute this, right? And you will see where it will be used later on. P0 is what? covariance of x0 with x0 given y0 equal to 1. How to interpret this? Is given y0 equal to 1, x0 is still random, so its covariance will be based on that randomness. So how to compute this? So it's we have the formula. Okay, so the formula is unconditional covariance. Once you see some relative variable, the covariance changes. Okay, the minus what? Minus the covariance of x0, y0 times covariance of y0 inverse times covariance of y0 with x0. Okay, and verify yourself. It's not definition. This verify yourself. This is some number 0.4, negative 0.2, negative 0.2, and 0.1. Where this formula come from? The conditional expectation formula. Okay, let me just make sure you see what I mean. This guy. Okay. Once you observe y equal to small y, okay, x is Gaussian. That Gaussian, whatever Gaussian has mean and covariance, it turns out covariance has this form. That's it. Okay, so okay, we have this guy. Then we can move on. We can move to the next step. The second step. All right. So I want to compute the best estimate of x1 given y up to time 1. What are they? It's the expectation of x1 given y0. y0 is still given. And y1, negative 1. Okay? y0 is given. Now time moves to time 1. You see another number of y1 at time 1. Okay? Given these two measurements, your belief about x1 also changes, right? And that distribution should also be run Gaussian. So we can look at this as if we can write like this is kind of recursive type of writing. But I can write like this. They are the same, right? y0, y1. This is called y1, capital Y1, right? Equal to 1, negative 1. All right. So how to compute this thing? So I will say 1 is the conceptually simple approach. It doesn't mean it's computationally simple. It's just for you to understand it's simple. To do this is like I will call this batch approach. It's the same as the first step. This is not Kalman filter, by the way, okay? This is one way to compute this best estimate of x1 by what? Find. So how we can compute this conditional expectation? Because these two, x1 and the capital Y1, are jointly Gaussian. By our assumption, all the things are jointly Gaussian in the world of Kalman filter setup. So we find joint distribution first. Okay, so it looks like x1 and y1. This is R3. No, sorry, how many? R4, right? This is the two-dimensional. This y1, this 2 is 4, right? But partition-wise, I will call this x1, y1. Okay, so I assume this should be jointly Gaussian, by the way. So this will be Gaussian. This will be expectation of x1, expectation of y1, right? So y1 is, let's write more explicitly this guy, right? That means you know how to compute this or not? You should be able to. I haven't derived it for you yet. Okay, now we have the covariance matrix, right? You can compute. This is the covariance of x1. Somehow you should be able to know how to compute this. It's fairly straightforward, although it takes some effort to find those numbers. Then x1 with y1, right? This is y1 with x1. This is covariance y1. Okay? So this guy is 2 by 2. Do you understand that? X is two-dimensional vector, right? This guy is 2 by 2. This guy is 2 by 2. 2 by 2 because y1 is also two-dimensional. This guy 2 by 2, and this guy is 2 by 2 as well. If you zoom in these 2 by 2, what are they? Those are covariance of y0. This is covariance of y0 with y1. I don't want to write it. It's terrible. Okay. Y0 with y1. This is the covariance of y1 with y0. Covariance of y1. Okay. So if you zoom in, that's that. We don't have to do this. So after do this, do you know how to compute? If I compute everything here, so then we can find expectation of x1 given y1 equal to 1 negative. This is just another exercise. Okay, what is it? Unconditioned mean plus covariance x1, y1, things like that. All right. What's the potential drawback of this approach? Right? It's not recursive, I would say. It's not recursive, not scalable. So as k increases, as k go to 1, 10, 100, 1,000, then the covariance matrix grows. It's huge, right? If you have let's say this y become y100, then you have 100 by 100 this part. Just this block is 100 by 100. So you need to keep inverting a larger matrix. It's not efficient, but it's correct. You can do it. Are you with me? So this is the same thing. This is give you the same result as Kalman filter. It's just computationally is not that efficient. Okay, but the conceptually easy to understand. So far, you already understand how to do this now. Okay, so the Kalman filter has another smartness involved. Okay, we just any questions by the way, the notation. 什么问题? Okay, all right. Now the second approach, which is recursive approach, which is just Kalman filter. Okay, that's the key idea now arises. Okay, so let me just say that. So after, I will say after. Let me write it down, right? As we write down, you can think as well. So after obtaining the same kind of argument as I always say, after obtaining y0 equal to 1. That's recursive, right? Let's start from the first one. So after we see y0 equal to 1, before I say x0 or x, now I want to estimate x1, right? So I only care about x1. So I will say after obtaining y0 equal to 1, both, so we're still at time 0, okay? Still at time 0. Okay, both x1 and y1 are random. I specify y0 already, but both x0, x0 is also random as well, but now I care about x1, okay? So both x1 and y1 are random. Can you see that? Of course, they're random. What their random distribution? I would say both of them are random and they are jointly Gaussian as well. Because conditional Gaussian is Gaussian. X1 and Y1 are jointly Gaussian, first of all. And the conditional on Y0, they're also jointly Gaussian. Okay, and they are jointly Gaussian. Okay, i.e., I have a formula like this follows, right? i.e., x1 and y1 given y0, that's the only confusing part, okay? Let's pay attention. Given y0 equal to 1, Yuntian, how do we interpret this ugly looking symbol?
We have observed y0 equal to 1, and but x1 and y1 are still
random, yes, and their random distribution is Gaussian, all right? We need to specify that. So what's the dimension of this random variable? In this example, it's 3, right? This state is 2, and the y1 is 1. I know the state and the y1 are jointly Gaussian. But that jointly Gaussian is different from before. It's after I see y0, I still think they are jointly, well, this is not I think, they are still jointly Gaussian. So they will, any jointly Gaussian, they will have a distribution, right? The distribution is Gaussian, is characterized by mean and covariance, but that mean and covariance will be expectation of y1 given y0 equal to 1, okay? Expectation of, expectation x1 given y0 equal to 1, expectation y1 given y0 equal to 1. Okay, that's the what? The expectation of the state and the output given your knowledge about y0. Of course, how do I move this around? Anyway, where we are here. Now inside here, I will have covariance of x1 with x1, but it's not the original unconditioned thing. It's something happened, will change my belief about x1. What happened? y0 equal to 1, right? Now this guy is y1 with x1 given y0 equal to 1. And this is conditional x1, y1 given y0. How do I move this guy? Anyway, let me zoom in. Given y0, and this is y1 with y1 given y0 equal to 1. I didn't write what y0 is, but you see what I mean. That's the covariance matrix now. Okay, now comes to the key part, okay? So suppose we know, let's say if we know everything in the above distribution here, okay? Everything in this mean and the covariance matrix, suppose we compute them. Of course, we know how to compute them. Then we claim expectation of x1 given y0 equal to 1, and in addition to that, y1 equal to -1. is, can you see that now? Okay, now I have some nested or recursive conditions, right? The first condition already happened. Given that condition, I know on average, I will see some kind of x1, I will see some kind of y1, right? If you want to use measurement to estimate the other, you always put them as a joint Gaussian distribution, right? So in this case, I'll claim the whole thing is this is just what? Expectation of this, I will call this unconditioned expectation because you haven't seen y1 yet. Okay? And plus the covariance of x1 with y1, but still given y0 equal to 1, times the covariance of y1 given y0 equal to 1, inverse times surprise. The surprise is -1 minus expectation of y1 given y0 equal to 1. Okay. The only hard part of Kalman filter is just this line. I think you see what it means, but maybe loosely or a little bit fuzzy, but over a few times of exercise, you will see exactly that's the case. Do you understand or you don't? You don't? Yeah, we have homework to practice you on that. Okay. Let me explain. Let me try to explain a little bit more. I'm not sure whether this helps you or not. Sometimes people like this. Sometimes people like, I introduce another notation that can somehow make things a little bit clearer, but other people may hate my notation. But let's try, okay? So let's define z equal to x1 given y0 equal to 1. And q equal to y1 given y0 equal to 1. There are so many equal, but you should know what it means, all right? This is the whole thing. Yuntian, that's my, can you explain this? Random variables. This distribution is the conditional distribution. They're also Gaussian. Okay? Are you with me? The time is at 0 now. I see y0 equal to 1. Then my distribution of x1 changes. And it's still Gaussian. And that Gaussian random variable, I define it as a new variable called z. Is that okay? This is okay, right? If I change notation, maybe something becomes simpler. And suppose we know z and q is jointly Gaussian. Do you think so? They are, okay? As I mentioned, you can always assume in the Kalman filter setup, everything is jointly Gaussian. Now I see what, all right? I see q. So then the jointly Gaussian, let's say that will be what? This is E of Z, E of Q. And this is what covariance of Z with Q, covariance Q with Z, covariance of Q. Okay? All right, if I change notation, everything becomes clean. Now what I'm asking you is that expectation of Z given Q equal to -1. What is it? Very simple now, right? It's the expectation of Z unconditioned plus covariance of ZQ, covariance of Q inverse, and -1 minus expectation of Q. Okay? This is simple, right? But you should be able to see this is what? Expectation of Z. Z is the conditional random variable. It's x1 given y0 equal to 1. This becomes the same thing like this, all right? This is the same thing like this. It just changed, I mean, if you just redefine the symbols, everything becomes clean to you, hopefully. And it may take some effort for you to see this is nothing but the expectation of what? x1, because z is what? Z is about x1, all right? And given y0 equal to 1 and y1 equal to -1, because q is y1. Okay. So if you like, I can change another notation. Is that expectation? This is nothing but the expectation of x1 given y0 equal to 1. That's z, right? And you're given y1 given y0 equal to 1. All right? So essentially, y1 equal to 1. So essentially, there's no given, it's just given y1 equal to 1. So overall, you have expectation of x1 given y0 equal to 1, y1 equal to -1. So you take y0 as something given already, and you can ignore it. The symbol here, you can ignore y0. You can presume that, okay, I'm leaving the world now with y0 equal to 1. I update my belief, everything become, I can remove this, but I need to update my belief, all right? I will define a new variable as z. Okay, on top of it, I assume I somehow get new information, y1, then that's how I compute this thing. All right. It will take some effort for the exercise. I think next time I will start with another example, somehow will help students to further understand it. And that's the derivation of Kalman filter, almost everything. Let's go through the steps. Okay, so our goal, let's repeat our goal. Our goal is to find xk hat. Okay, and also because each time at a given yk, xk is Gaussian. So Gaussian has what? You need to keep, how do you represent Gaussian? You need mean and covariance. Okay. So as I mentioned, the Kalman filter is a recursive way to update this. So we need not only that, we need to know how to move from k to k plus 1, right? So that's one step will be go k. First of all, this recursive way, you need to know how to start, right? We can compute this guy. So sometimes these are given. I will say sometimes x0, p0 are given, directly given to you. Okay, the mean is this, and the covariance this is that. It's directly given directly. If not, okay, we compute, right? We compute. We just need to compute what? We just need to compute the expectation of x0 given y0. Okay? Well, I didn't specify what number that's given. And also, p0 is covariance of x0 given y0. That's typically easy to compute. Okay, you can use one formula, the conditional expect. They are jointly Gaussian, right? That's the starting point. And given xk and pk, how do we compute x? How do we move one step forward? If we know this, then everything is done. And the whole process can be divided into two parts. Okay, just for you don't have to do this derivation. Sorry, you don't have to divide this into two phases. If you know how to directly compute them, that's fine. But This will simplify the discussion, and it's correct, so we will, but most people will do this, right? They have two states. Suppose now I have given time k, xk is given given measurement up to time k, xk is random. Its mean is xk hat. Its covariance is pk, right? What I want is I want to go here. That's our goal. I want to say given measurement up to k plus 1. Xk plus 1 is also random. Its mean is xk plus 1 hat. This covariance is this guy. I want to move from here to the k plus 1, and I will insert one stage to simplify the derivation. Okay, the first step is xk plus 1 given k hat, and the pk plus 1 given k. Right? So k plus 1 given k plus 1. This means that, right? And this guy is k given k. So both the things before the bar and after the bar need to be updated. So I will do that one by one, right? So I first update the one before the bar. This is so-called prediction. So I only have measurement up to k, and I predict my best estimate at k plus 1. And this step is called, the most important and the hard part is the measurement update. Okay? So now this is only have measurement up to k, right? Now I need to go to measurement up to k plus 1. The only difference is what? I have new measurement. I need to change my estimate. So, okay. Now let's first see the simple step, prediction. So that's, and we are given here, okay? That's our starting point, this one. Suppose we know this. Now let's see how we can do the prediction. What we want is k plus 1 given k plus 1 given k hat is expectation of xk plus 1 given yk. How do we compute this? So the expectation of, we need to relate k plus 1 with k. So that will be a xk plus b of uk. I dropped the index for a, b, okay? They're deterministic, whatever those index, it doesn't affect our derivation. Omega k or wk given capital yk. What is this? Can I move this out? It's equal to a times expectation of xk given yk plus b times expectation of uk given yk, which is expectation of 10 is 10, right? A number is number, it's a deterministic thing. So plus expectation of wk given yk. Okay, is this 0? Okay, now my claim, or Yuntian said, it's independent, so it's 0. Is that true? I don't think so. Wk and yk are independent. Okay, so independent, wk, independent of yk. All right, everything is independent because process noise is independent of yk. All right, now what does this mean? They can tell me that expectation of yk equal to expectation of wk. Right? Why? Because density doesn't change at all if you know it. And this is 0 because of our assumption. Okay, independence doesn't tell me this guy is 0. Okay, the covariance is true, but for this expected doesn't. But we assume that our process noise is 0 mean, so that's why. Okay, this guy's here. What about this guy? Xk hat. All right, so overall I have A xk hat plus B of uk, no more. Okay, I have this formula now. Okay, let's call it 1. Like a linear system now, right? This equal to this. Why I can break this? That's the property of expectation. And the conditional expectation is expectation. You don't need to, be confused by those given things. It just tell you the density function is not the one without the condition. It's somehow changed. You just need to use the right density function. Everything become a plain expectation. Okay, let's say pk plus 1 given k. That's our covariance, right? So it's a covariance of xk plus 1, xk plus 1 given yk. How to do this? Covariance is, let's see, so that will be let's write it down, okay? Expectation, covariance is expectation of what? Xk plus 1 minus the expectation of that, right? The expectation of this given this, it's xk plus 1 given k hat, okay, times xk plus 1 minus xk plus 1 given k hat given yk. Oh, sorry, this is a transpose, right? Okay. Overall, I can plug in things. That will be, this is A xk plus buk plus wk. That's first term. Minus this guy we just computed here. So it will be A xk hat minus b of uk. That's my first parenthesis. Times this guy itself, transpose, right? It tells itself, this guy. Then, of course, everything is given. Given is given, right? It's happened already. So overall, I have this got cancelled with, so that's why u doesn't matter, right? That much at least. So that will be what? Expectation of A xk minus xk hat times this guy, plus, let's not worry about those cross terms first. Let's look at other terms, okay? Times xk minus xk hat A transpose given yk, that's my first term. Okay, I'm missing a lot of terms yet, okay? I will this guy minus this guy, right? And I group them and times whatever the corresponding term in the transpose. Okay, so I put this and also has some cross terms. So for example, I will have expectation of this omega k times omega k transpose given yk. Right? And also have expectation of cross term, this minus this, times the omega. So it will be A xk minus xk hat times omega k transpose given yk. Okay? and plus expectation of omega k times AXK. So XK minus XK hat transpose A transpose given YK. Okay. Well, you should be able to write down. It's very simple. They just take some effort. So the first question I'm asking you, what is this? If you move this out, move this guy out, what you get is A times PK. PK is just the covariance of XK given YK, right? Times A transpose. That's the first term. Plus this term. Is this 0? Is this 0?
No, it's not the covariance of WK given
WK is independent of WK independent of YK. Tells me this guy equal to WK transpose. Okay? And this I will say this is nothing but QK. The reason is because I assume WK is 0 mean. Right? Only when 0 mean, that's QK. If it's not 0 mean, if everything is not 0 mean, then we have other terms to subtract. We still have the same conclusion. So overall, this is QK. So this guy is QK. Now I will say this guy is this random. What is it? This is 0 or not? Yes, this is the covariance of XK with omega k or WK, and this is 0, right? This is 0, and this is 0 as well. Okay. All right, so overall, I have this one-step prediction formula. This is our equation 2. This is 1. This is 2. Okay? That's the Kalman filter. If you look at, I'm not sure the notation. You look at Wikipedia, whatever, you see those formulas. And you can implement this formula very easily. I will show you code next time. But to understand them, that's the effort we have taken so far. You just try to understand them. Are you with me? What we're doing? Prediction. We are trying to find the best estimate of xk plus 1 at given measurement up to time k. Okay, because everything is Gaussian, we can do this very easily. The second step is the hard part. We have 2 minutes, right? Or 1? 1 minute. We can finish this? No. I don't think so. All right. But I will give you some homework to practice. Next time, I'm sure I will test you on the quiz now, all right? So I keep missing my quiz. All right. Okay, let's get back to our lecture. So first of all, the last maybe 2 or so weeks, we cover quite a bit about probability and also for the purpose to understand or to fully understand Kalman filtering. Okay, and last week we were almost done for the derivation of Kalman filtering. Let me briefly recap a little bit. So Kalman filter is dealing with these stochastic linear systems. Our goal is to try to estimate state given all the measurement. According to the what? Minimum mean square estimation theory, and all we need to do is try to compute the conditional expectation of x given all the measurement. Okay. As I mentioned, the Kalman filtering assumption is that everything is linear Gaussian. So every state, all the state at any given time, and all the y at any given time, they are jointly Gaussian. Okay, so we are living in a Gaussian world, so we can easily compute conditional expectation. Okay, if it is not Gaussian, it will be pretty hard to compute them, especially for high dimension. Based on this, so I want you to keep in mind we're just computing this. Okay, so it's completely a what? A probability problem. All right, a lot of filtering and signal processing and communication networking. I mentioned quite a lot applications, right? And I didn't give you a detailed example. You will eventually see. Hopefully, I will show you some example today. They're just trying to estimate something given, estimate a hidden variable given measurement. Okay, all of them is about doing this, and eventually they're just trying to compute conditional expectation or some kind of function of the posterior distribution. Okay, the key you have to remember is that at any given time, where is it? Okay, before doing that, you should know the definition of those notations. At any given time, xk given capital Yk, at all the measurement up to k. Xiaohan, how to explain this? Is this a random variable?
Yes.
What kind of random variable it is? It's Gaussian. All right, we are living in the Gaussian world. It means this is a given Yk, xk is still random, and its distribution is Gaussian. If you want to describe a Gaussian, what do you need? A mean and covariance. What is mean and covariance? Our notation means this mean is what? Xk hat, right? Covariance is pk. Okay? I hope you truly understand the meaning of these notations. There are more sits up front. Okay? You see what I mean? All we are doing is try to update this as k increases. Okay, we are deriving what the mean should be based on the system dynamics and based on our modeling assumptions. So all we are doing is to make sure we know the mean and the covariance, so we know exactly everything about the distribution of xk given yk. Okay, so last time we mentioned that typically we need to do this iteratively or recursively, and this is xk hat and pk at time k, and our goal is to compute xk plus 1 hat and pk plus 1. Right. We break up this step into two intermediate steps. The first one is called prediction, for which there's two index, right? K given k to k plus 1 given k plus 1. Both of these two things have different meanings, all right? So these two need to, we just need to change them one by one, all right? The first one is prediction. We fix the measurement. We only predict the next step. So this is what I think we were done last time on this step, right? If you don't remember, I think everyone in this room should be able to derive this. This is the simplest step. This is a very simple application of what we were doing. It does not even involve Gaussian. All right, this step is simple. Prediction step is simple. The hard step is the measurement update. Okay, so we give an example to let you see a flavor of this measurement update. This example, I'm not sure how many of you review this example. I think you should review this example, try to understand everything, and then the Kalman filter step will be simple. Okay, let me summarize, add one more slide to make sure everyone can understand. I would say the key for Kalman filter measurement update step. Update step. Okay, the key for that, let's even try to move to a more generic problem with what we're doing, okay? I don't want to kind of confuse you with those sub-indices or xk hat. Let's just think about a generic problem, okay? I would say key, I would say just key, that's fine, okay? Let's assume we have x, y, and z, 3 random variables. Okay, let's somehow jump outside of the a common filter setup. Let's use these 3 simple notations. Are jointly Gaussian, all right? Jointly Gaussian. Okay, so I will say x, y, and z. If we view them as a big vector, and they are distributed as a Gaussian, so with mu x, mu y, mu z, and some covariance matrix, you know those numbers, right, in the matrix. Suppose they are given, right? So the question I'm asking, okay, this question is related to the fundamental nature of the measurement update step, so that I'm somehow explaining it separately. So the key is that I want to make sure, I want to compute my expectation of x given y equal to y and given z equal to z. There's 2 things given. Okay, there's 2 things are given. Both y I know, both z I also know. Do you know how to compute this? That's very simple for you, should be, all right? Maybe I'll give a test or a quiz. So this should be very easy for Gaussian because a direct approach should be easy, okay? I would say direct approach. I mentioned this a little bit last time as well. Okay, we will just view everything, whole thing, as a big vector, okay? And try to compute what? Try to compute the expectation of x given y and z equal to y and z, all right? This given we view as single given, right? They're given at the same time and specify the value. But this vector is fine, all right? And using the conditional Gaussian formula we discussed and practiced many times over the previous lectures. Okay, but we can compute this way. That's called, I would call that batch approach. Okay, we view these 2 things are given together. Okay, but Kalman filter is really about recursive. Things like recursive. And the first step, I'll try to relate, okay? Suppose I can compute x given y equal to y upon knowing y equal to y. An event happened, y equal to y, right? Then I update my belief about x, and x is still random. I can compute this, that's fine. Because x and y are also jointly Gaussian. Let's forget about z, x and y are jointly Gaussian. You know how to compute this, right? This is also simple. Now the question is, the second step is, I want to further update. Y gave me some update about my belief about x. Now, in addition to y, I receive z, right? Upon update x given to y and z equal to z, upon knowing the value of z equal to z. You see the difference? I break this into 2 steps. First, I compute y as I know y, right? And then z come in. I know z as well, but I don't want to recompute them. I want to use, the key is that I want upon knowing this, using x given y, right? Recursively. using my previous knowledge about X after receiving Y. That's the key. The result will give me the same result. These two, X and 2, these two approach, there's too many 1 and 2, sorry. There's, let's call it A and B. Okay, this 1 and 2 should lead to the same result. It has to be, okay? But the key is that in this way, I can keep updating once I receive new measurement. Last time, the example I gave you, I already tell you how to do this, but I want to explain that a little bit more. Let's think about this as the following, right? I have X, Y, and Z. They are jointly Gaussian, X, Y, and Z. There is a covariance of X, right? Covariance of XY, covariance of XZ, right? Covariance of Y. You know how to fill up this covariance matrix. Okay, that's original. Before I know anything, this is what my knowledge about these three random variables. Now an event occurred. Okay, event occurred. Somehow I know Y equal to Y. I know Shenzhen or Guangzhou temperature equal to 20 degrees today. Today is cooler than yesterday, right? So what happens? Then I'm into another kind of domain. I know now I'm living in the world that I see something already happened. That completely changed my belief, right? I'm inside a box, and this box, after Y, I see Y equal to Y, I will say X and Z, do you know them? I know them, but I don't know them for sure. They are still random. What's their distribution? It's still Gaussian. Outside this, of course, X and Z are Gaussian. Now Y equal to small y, right? I see that. Under this assumption, under this condition, X and Z are still Gaussian. Are you with me? Okay? And this distribution will be still Gaussian. Gaussian characterized by mean and covariance. What do you think its mean will be? Is this mu x? No, I know Guangzhou is 20 degrees today, so modified my belief. And what this should be, somehow the mean is conditional mean, right? Now I'm living in the y equal to small y world. Okay, everything has changed. Okay, my belief is still in this world, and I also know mu of z is also given y. All right. Okay. So for sake of simplicity, I would ignore this a little bit. I will use a different notation. I will call this mu x tilde and mu z tilde. To distinguish, this is not different. Okay? Now I have covariance tilde x, covariance tilde xz. Okay, this covariance matrix become 2 by 2 if x and z are scalar. Covariance tilde x and z. Okay, and this is covariance tilde z and x, and covariance tilde z. You see, right? If I change this, everything becomes different. Okay. Now let's look at this again. So now what happened next is that, okay, another event occurred. I know another event. What is z equal to z? But this event occurred after I know y equal to y. So I'm now in the world, this box. y equal to y world. So then I'm going to ask Su Yuan. After this event, is x and z are still random? X is still random, z is not. Z is known, all right? Z is small z now, okay? So x is still random. What's the distribution of x? Gaussian, right? So it's Gaussian. I will call this mu of x tilde tilde, all right? Everything becomes different, right? So then this is covariance tilde tilde x. This will be my what? Expectation of x given y equal to y, z equal to z. Okay, but how do I compute this? By using here, not jumping outside. I can directly compute this from here, okay? But I can also do recursive, this nested loop, okay? First I jump in the box. I'm living in the world of capital Y equal to small y. Then I jump into a smaller world that, I further know more information, capital Z equal to small z. Then I'm here, right? So what do you think about this? Mu x tilde tilde equal to what? Depending on where you write this formula, if I write this formula inside this box, will be mu x tilde, given this, right? I'm treating this, right? So inside this bigger box, this nested box, okay? Characterizing the information available to you. Plus what? Covariance of x, z, tilde, right? Covariance tilde z inverse times z, small z, sorry, the capital Z small z is a little bit confusing, but this small z times mu z tilde. Are you with me? So if I'm computing after if I here, so I know this formula using the previous estimated x and z, so that will be my formula. Okay? So that's the recursive update. If you look at this, this is what? It's the expectation of x given y equal to y. This is covariance of xz given y equal to y. Right, the tilde means here. So after you inside the y equal to y box, you zoom in, you apply the formula again, but you should use the one that before, right before you see capital Z equal to small z. Okay, so what does this mean? I typically call it surprise, right? This is I will now call it additional surprise. Surprise, okay, due to z equal to small z. And this additional means what? Beyond, I know y equal to y. Y equal to small y give me some surprise, all right? But that surprise is already considered in this distribution. Now I'm zooming in further. I got this distribution. I hope you can think a little bit more clear through this way. Some people prefer this way, some people prefer just seeing the formula. Either way is fine. It's clear to me, but they require some time to practice. So now I'm asking you, if I do this loop, if the event is given like this, so suppose expectation of x given, first I see z, then I see y. Is this the same as this? They are the same, okay? Given is given, known is known. So this all means, this doesn't have an order, okay? You can put either way you want. It just means those things you know for sure. It doesn't matter how you know it, which one you know first and second. Okay, it's just those numbers are known. These two are the same. Okay, you can compute different ways, they will give you the same answer. I think in the homework I asked you to do this. Did I? If I didn't, then I need to add more homeworks. You do these two ways, both in the recursive way, and you see they are the same. Okay? Okay, now let's get to our measurement update. if you know this fact, okay, now we can easily explain the measurement update step, which is the only hard part for Kalman filter. Okay. So you should first know our purpose. So our purpose now is that what? We want to compute xk plus 1 given k plus 1. And what we are given now, what we know now is the expectation of xk plus 1 given xk, yk, and its covariance. All right? And how to find the mean and the covariance of the new thing. That's the update equation. Okay, I will say again, this two approach, right? I'm going to repeat a little bit. Approach 1 is batch. Okay, we can do this find joint of everything up to k plus 1, right? So the joint will be xk plus 1, let's see, and the yk and small yk plus 1. You know my notation? This is state. This is all the measurement up to time k. This small yk plus 1 here means the y at time k plus 1. Okay? And we can find this joint. I wouldn't write down the notation. It will be very complicated. Depending on how many k you see, it will be a very large covariance matrix with a long vector, right? Then we can use conditional mean formula. Because we know it's Gaussian, right? Conditional mean formula to compute what? Expectation of xk plus 1 given yk, and in addition to that, also given small yk plus 1. That's the best way. You just treat everything as giant Gaussian random vector, then given part of them, it's still Gaussian, you can use the formula, right? But that's not our goal. Our goal is trying to do recursive. So approach 2, as I mentioned, through the abstract example, I hope now at least you are a little bit more familiar with it. Recursive. Let's do recursive. Using what? The previous result. Xk plus 1 hat given k. We know it, right? Where do we know this? From the prediction step. And this is k, pk plus 1 given k. Using previous step to compute the new one, which is xk plus 1 hat and the pk plus 1. So in this case, first let's find joint. We want to rely on our previous measurement, updated belief, right? So let's see. First, we can find the conditional joint, okay, which is, I only care about current xk plus 1, a small xk, yk plus 1. They are related, right? So what I'm doing now, I'm using yk plus 1 to estimate xk plus 1, right? They are related, but given yk. So yk is given at time k. Now it's already in the here, right? Capital yk equal to small yk, and then it's already jumping to the next box. And this is at time k, at yk given, capital yk is given. xk plus 1 and yk plus 1 are still random. Are you with me? You don't know them for sure yet. Okay, later you will know one of them for sure. So they are jointly distributed. And their distribution is, Xiaohan? Huh? 云天.
Jointly Gaussian because it's a linear transform of xk plus.
They are jointly Gaussian, of course. Yeah, right? Conditional Gaussian is Gaussian. So they are still random. They are jointly Gaussian. I need to find their joint Gaussian distribution, which is, let's say, the expectation of k plus 1 given capital Yk. This is the expectation of Yk plus 1 given Yk. Right? Any questions?
I think it's a linear transform, so it's
Okay, in linear Gaussian case, in Kalman filter, everything is jointly Gaussian, no problem, right? I'm just trying to say, if we specify all, this is what? This is from Y0 all the way to Yk, right? If I specify all the measurements up to time k, I don't know for sure xk plus 1, and also don't know for sure about yk plus 1. Their distribution is still jointly Gaussian given yk. Okay, they're jointly Gaussian, so I can compute their, all we need to characterize Gaussian is what? Mean and covariance. So the mean, let's denote this mean is this, and this covariance, right? So there's a covariance of xk plus 1, I'll just call it that. Maybe that's fine. K plus 1 given yk. Everything is given yk. Covariance of xk plus 1, yk plus 1 given yk. I hope you can fill up the rest two terms. Let me write it down. Yk plus 1, xk plus 1 given yk. And this is the covariance of yk plus 1, yk plus 1 given yk. So at this k, at time k, xk plus 1 and yk plus 1 are jointly distributed. All right? So then I want to say, now how do I compute these, the additional ones? I will say this is expectation of xk plus 1. If you want, I can define new variables, but I don't think that's, so at time k, let's define, okay? If we define, let's call it z. I think in the note I also do this. Xk plus 1 given yk. And the w equal to yk plus 1 equal to yk, given yk. What does this mean? Z and w denotes the randomness of x, k plus 1, and small yk plus 1 given Guangzhou temperature at time k plus 1. So given capital Yk plus 1, the history up to k, both are random. Each of these randomness, I denote a new random variable. It's the same, all right? It's z and w, right? So I know z and w. If this helps you better, a Gaussian. Then this is this, this is that, okay? So you can view them as, if you don't like this conditional notation, you can view them as a new variable, okay? Conditional Gaussian is Gaussian. Conditional probability is probability. Conditional density is density. If you don't like the conditions, you can just remove them, define a new variable, okay? You just need to make sure the density are computed in the right way. Okay, then I will say expectation of z, which is this, given w equal to yk plus 1. By my notation, this will be E of z plus covariance of z and w, covariance of w inverse times yk plus 1 minus expectation of w. Okay. By my early notation, this is equivalent to say let's not do define. This is nothing but Z is what? Expectation of my expected measurement given YK. All right?
Z should be X.
Oh, this would be X, sorry. This is XK plus 1. Okay? So given capital YK, XK is random, its mean is this, right? And then I need to know how Z and so XK plus 1 and YK plus 1 are related. But the relation I only care is relation given the condition YK is already specified. Okay? Times the covariance of W. W is YK. Okay, with YK plus 1 given capital YK. Inverse, right? And then times the surprise minus expectation of YK plus 1 given, given capital YK. Okay, let's call these terms different. This one is my term 1. This guy is my term 2. This guy is my 3. And what else I need? This guy, 4. If I know how to compute this 4, I know how to do this update. Okay, before you see any new measurement, this is your best estimate of xk plus 1. Okay, because that's, you already know by up to time k, before you see any new measurement, that's the best. Okay, and your measurement will provide some information. Okay, so it's possible. Okay, it's possible that after giving yk, then the small yk plus 1 is very, very much deterministic, have very low variance. That's possible, or have larger variance. That's also possible. So that should be normalized, and how they are related. And those relations should be specified given capital YK. Okay. Now let's do one by one. Do you have any questions about this? I think we practiced many, many times, several times already. It's just nested conditioning. Let's do one by one. The first one is what? What is 1? Expectation of xk plus 1 given yk, but by definition, this is what? Xk plus 1 given k. That's my notation. That's given, right? Given by prediction step. This is already computed. We already computed this. This is known. That's my best guess before I see a new measurement. Okay, that has not related to measurement update. Now let's see how we can do the measurement update. Let's first compute. I don't think I have time to derive everything, so let's pick a few. Let's do the simplest one, which is the 4. Okay. Expectation of yk plus 1 given yk. What is it? We are trying to relate it to x, right? So that's the expectation of c xk plus 1 plus d uk plus 1 plus vk plus 1 given yk plus 1. Oh, sorry, given yk. Okay, because it's the expectation, I can move the constant things out. So that will be c times xk plus 1 given yk plus, is this 0?
No, it's constant.
It's constant. Expectation of I wouldn't say constant, sorry. Expectation of a deterministic thing is that particular deterministic constant, right? So it's d times uk plus 1. What about expectation of vk plus 1 given yk?
0.
It's 0. Okay? Little yk plus 1 is independent of capital YK. The new noise independent of previous noise. Okay, that's the assumption. And because we assume it's zero mean noise, if it is not zero mean, you need to subtract it, the mean, okay? But because we assume it's zero mean, that's zero. I hope you are fine with this part now. So this will be our xk plus 1 given k, right? So it's hat. Cxk plus 1 given k hat plus d of uk. That's our, let's pick one more. Let's do 2. Okay? So that's covariance of xk plus 1, yk plus 1 given yk. By the way, what's your understanding of this term?
What do you expect to see after
Yeah.
after you have the yk, the y value of yk?
Uh-huh.
But this may be different from what you really see as yk.
Yes. Okay. So typically, maybe yk, let's say Shenzhen temperature today. All right. And this capital YK is Guangzhou temperature up to yesterday. Right. And you see yesterday, temperature is pretty low, for example, 15 degrees, suppose. All right. I don't think that's the case, but anyway, let's suppose it's 15 degrees. Then somehow you lower your expectation of YK plus 1 today as well. Right? But this is on average, you expect to see some temperature of Shenzhen today. That's the best guess you can have, right? But later on, you may see a surprise. But that surprise is in addition to the surprise you already got from yesterday. So let's compute this covariance xk plus 1, yk plus 1, given capital YK. This is covariance of xk plus 1 with what? Yk is cxk plus 1 plus d of uk plus 1 plus vk plus 1, right? These two terms given yk. Okay. Okay, then you can do this by each of them, right? It's like a multiplication. It's indeed a multiplication. So why I carry this all over the place? Of course, that's condition. That means the density is the conditional density when you do the integration for computing expectation. That only means that, right? So this will be, what is this? Can you tell me the result? So covariance of xk plus 1 with xk plus 1 C transpose. That term, right? So this will be our, we cannot. Given is like the box I draw, okay? Given that everything changed, your belief about those variable changes. So that should be carried. This will be what? Pk plus 1 given k, right? That's the definition of pk plus 1 given k times C transpose. Okay, that's the first term. Second term, what is it? Covariance of a constant is the constant? Is 0. Okay, covariance doesn't, this part is 0. What about covariance of xk plus 1 with vk plus 1? It's also 0. They are independent by our assumption, so this is also 0. Okay, overall, I have this term is pk plus 1 given k times C transpose. Very simple, right? That's our second term. Oh, I don't have space, so the third term I will skip. I don't think that makes more sense. You just compute this just like, I think you can do the calculation. We're done. This is common filter. Let's look at the formula. I will post the complete derivation. I don't think you care that much. I care, but I want you to at least go over the complete derivation every step, so you know roughly what's going on. And I wouldn't test you on the exam about derivation of the entire Kalman filter, but I will I will test you on understandings. Okay. So if you look at the formula, let's look at the formula. Okay. This is the prediction step. You start with the estimate. I think all of them should have a hat. Okay. Where is it? That's it. So this is a hat. This is a hat. It didn't show correctly. This should be hat. Okay. So you start from some time with the best estimate you have at this stage. Then you do prediction. These are the prediction formula we derived last time. Does this look similar or familiar to you? These are linear prediction, just almost like a linear system, just ignoring the noise. This is the covariance update that we derived last time. Okay, and today we have been deriving measurement update. Look at the measurement update equation. What about this term? This is the surprise, the new surprise, the additional surprise, this particular step. What about, let's do some different color. What about this term? This is what? This should be, sorry, this is hat as well, right? This is expectation of yk plus 1 given capital YK. Cxk predicted minus, this is plus, right? If you have two minus sign. And you can look at your derivation, or our derivation before is this, right? C times this plus du. Well, the time index doesn't match that much because here we from k to k plus 1, that formula, it was from k minus 1 to k. That's the only difference. D of uk plus 1. So this is expectation that, right? If you look at this surprise term, it's hard for me to adjust. This term, right? That's a surprise term. That's so-called innovation. The yk minus the conditional expectation of yk plus 1. Sorry, the yk plus 1 minus the conditional expectation of yk plus 1 times how noisy that measurement is, and times the correlation between the y and the state. And these 2 and the 3 multiplied together will be our Kalman gain. Okay, Kalman gain matrix. So you look at this innovation term. This k is what? It's some constant times or some gain matrix times the surprise, and then gain matrix have the form of what? This guy. What is it? This would be covariance. Just the covariance update, sorry, conditional expectation formula. This will be what? Covariance of xk plus 1 with yk plus 1 given capital YK. Okay, this term, I mean this term. Is it?
Yeah.
So the reason I have ck is that allows c to vary every time step, that shouldn't bother. It's just this one. We just derived. And the thing we're missing here is third term. Can you guess from the result? What is it? This is our third term that I didn't compute for you. I don't have space. It's very easy for you. Okay? What's truly missing from my derivation is this step that I didn't compute for you. That's the covariance matrix update. Following the steps I post online, you should be able to understand this as well. Now, I think you should have a very good understanding, maybe after some practice, of every single step in the Kalman filter. And I'm going to show you examples today, and you will see the codes are only less than 10 lines, as I promised you before. But if you don't understand them, you can only call packages. But now you understand them, you can do a lot of different things, including one thing that I hope I can cover today, is the extended Kalman filter. RK is just R for us. So the notation is here, right? Okay. Our notation is, this is that, sorry. Head, everything given is head. This is head. RK is here. Is the measurement noise covariance. This is the process noise covariance, QK. I allow them to be time varying. Okay, each time step, I need to multiply by A and B, but at different time K, I can multiply them by different A and different B. And their noise can have different covariance matrices. And derivation will be exactly the same. I just didn't carry over those subindices throughout the derivation. Okay, that's the whole notation. So typically, if you learn from online or other class, all you need is this. Okay, we can finish within one lecture. Now, I think you should know what exactly is going on and how to generalize them. What are the keys? Keys, I need to know the conditional distribution. And because it's Gaussian, so my conditional distribution can be characterized by mean and covariance. And if every step is conditional distribution, then next step will also be Gaussian, right? If the current step is Gaussian, next step is also Gaussian, right? So that's the Kalman filter whole algorithm. And I think you need some time to practice. Let's take a break and we'll come to a few examples next lecture. Let's continue our discussion. Okay, I think you should understand every single step in this update algorithm now. And now we're going to see a numerical example about Kalman filter. But before that, I want to mention one thing. So in simulation, any simulation environment, MATLAB or Python, you can generate random numbers. Okay. So for example, I can generate, I can let x equal to, for example, MATLAB notation, run n. Anyway, so I can generate 2 by 1. That means this is what? A Gaussian random vector. Okay, this all means is that x1 and x2, they are both uniform, they are both Gaussian random number and with standard deviation equal to 1 and also 0 mean, okay? But if I put them together, they are independent as well. If I put them together, that means 0 mean. What about covariance matrix? If you think about them as random vector, it's 1, 1, 0, 0. Okay, that's the meaning. You can either generate them separately, and they're independent, so that's the covariance are 0, right? This is what covariance of x1 itself. Okay, so I can do this, but if I want to generate random vector, suppose I want to generate v according to this is 0 mean, and also with some covariance matrix R. How do I generate this? Modify x. So I can let v equal to square root of R times x. That's it. This is the matrix square root. Square root, which is only for positive semi-definite matrices. Okay. If you read my linear algebra review, positive semi-definite matrices. Okay. I think I explained a little bit about this. You can still take square root. Do you know how? Why it's the case? Or if you don't like this term, this will be like this. So it's R square root. It's the same. It's more, it's a matrix, by the way. Okay, it's just a matrix, R times this equal to R. You cannot take square root for negative definite matrices. Okay, so you will not have a kind of a real matrix anymore. So this is a square root matrix. You can just call square root of matrix in Python or MATLAB. That will give you that. Why is this case? Because covariance of V with V now becomes R transpose covariance of X times R transpose, right? And this is a symmetric. Covariance matrix itself is positive semi-definite. That's one property that we discussed. Is also symmetric, right? So transpose or not, they are the same. So that will give you that whatever R times identity, which is R. Okay, that's a typical way we generate random variables vectors with given covariance matrix. All right, with this specified, let's look at a Python example. This is the Kalman filter example. Let's take a quick path of it, right? Before that, I'm here trying to, what is it? It's already run. Let's clean out. Let's see. So here, I'm generating a matrix. The reason I generate like this is I just want to make sure I can specify their eigenvalues. I do a kind of random kind of T matrix, T diagonal T inverse, give me A, and that's so I know the eigenvalues of A are kind of stable A. All right. Here it's hold on. This is it's called process noise, right? Process noise. Specification is 0 mean and with covariance Q. I can specify how large the covariance is. That means how noisy this noise is, right? And what about R? R is here. R is here. So this is measurement noise. Measurement noise. And I specify some dimensionalities that I need to initialize my vectors. And so first of all, I'm trying to generate, here this part is, the goal is to generate data. In real experiment, you don't generate data, you get data, right? Here I generate data for testing purpose. I'll say generate data for testing. Okay, I initialize everything to be 0, and that just makes sure I have a matrix. And the way I arrange this matrix is X is a column vector, and each column represents a two-dimensional vector, right? And N is the number of steps I generate data for. Okay. Now I generate data. So here has nothing to do with Kalman filter. In reality, you would directly have the measurement. Here I just generate data. The way I generate data somehow follow my modeling assumption. First of all, I generate measurement noise. You see this thing? Square root M. LA is not Los Angeles, it's this guy, okay? Spice linear algebra package. This is LA dot square root, but M means matrix, okay? And times the random numpy random dot run n. That's somehow.
I have some question for the data generated.
Yeah.
They are not actually follow the model because xk is already added noise, and sk plus 1 is generated based on that.
No, sk plus 1 is generated based on other different. Each k will have different noise. They are all independent.
So my question for Kalman filter is the xk plus 1 and the xk, their real value should follow a perfect
They don't have to. They don't have to. But here is perfect. Here is perfect. If you don't, if you have a question, we can talk offline about this, right? So at process noise and measurement noise, and this is a measurement, Cx plus measurement noise, and this is state update. I don't have a control here, okay? We don't have control. I just didn't put a control for simplicity. And each k, each time step, I generate a new noise. This noise somehow is independent from previous generated noise. Somehow this is our, matches our assumption. If it doesn't match, it's fine, okay? X hat, that's begin our setup for, let's say, setup notation of variables for Kalman filtering, okay? X hat, X predict, K is the Kalman gain, and the P is the covariance matrix, P predict. I'm not sure whether you can, this is X hat, this is a P. And this is a P predict, this is X predict, X hat predict. I didn't say X hat predict, I just say X predict. All right, I initialize, I random pick a noise in this case. Random pick initial guess. It doesn't matter, it will eventually convert to the true one, okay? And I also random pick a covariance matrix at the beginning. Okay, I will explain this a little bit more after we see this example. And n is 100. Yes, n is 100. I don't need to redefine it here. Now I start Kalman filter. Let's count 1, 2, 3, 4, 5. 5 steps. That's the essential code for Kalman filtering. 5 steps. Of course, you need to set up variables. So don't be afraid of if you call package. There's some package called Kalman filtering. You call it, you don't know what's going on inside. And this may be what's going on inside. Just 5 lines of code, right? And X predict is A times X hat. What we are doing here, this is this step. Okay, X predict is A X hat plus BU, U is 0 in this case, is just this, right? And then I do AP A transpose plus Q. So P predict AP A transpose plus Q. Now we can do the measurement update. We first compute Kalman gain. That's just P predict C transpose whatever inverse. Okay. Then XK. The next one is what? Is before you see the measurement, your best guess, which is the predicted one, times the Kalman gain times the surprise. Okay. And this is exactly what's going on here. Times the surprise, and then I update the covariance matrix to the next step. Okay, that's Kalman filtering. It will be very quick. Then we plot. In this case, I think X is how many dimensions? It's 3 dimensions. So I choose three things. Let's run it. So that's the. I think S2 is a little bit worse than the other cases. This is pretty good. It doesn't matter what I gave as the initial guess. Let's say this may be 0 is almost correct. I think I also use, I don't know why is this. Anyway, let me use my mouse. Let's use 1s, okay? It's wrong, right? It's completely wrong. My initial state was 0 when I simulate generate data. I think it should be okay as well. Let's see. It's still roughly the same, all right? It doesn't matter. You can see initially it's a big guess. As you see more and more measurement coming in, it follows the structure. It follows, it's kind of approaches the true state, okay? What really affects the performance is the following. It's maybe, let's say, measurement noise. Let's say maybe we have more measurement noise. Just 1 times this. Okay, so if you run it again, it's become less accurate because the measurement it's too noisy, right? You don't know what the true state is, but still doing okay, right? And of course, the process noise we can change them, but the more noise you have, the less accurate the system would be, right? I think that's about Kalman filtering. I want to briefly mention one thing in this case. Typically, here, you see the Kalman filter is a recursive step, right? From estimate to the predict, from predict to the measurement update, then you go on and on, right? So this is a loop. We can start this loop from either entering here. Entering this measurement step, you need what? You need the prediction and the predicted covariance matrix. Entering this prediction step, you need the best estimate, okay, without the prediction. So typically, this one is typically easy to specify, okay? So for example, x0 given -1, it's given nothing. It's almost the same as this will be, expectation of this will be just expectation of x0. All right, you can input this guy to this and the covariance of x given -1. -1, suppose you have your first measurement come in at time 0. Given -1 means you didn't specify any information. You haven't given anything, it's unconditioned. So that's the initial distribution. And this will be the covariance of x0. Right? You can completely specify this. For this part, this guy is what? This guy, sorry, this is hat. This guy is expectation of x0 given y0, right? And y0 is given, you need to compute a little bit before you can actually start the process. Okay, but I would say, you see the simulation? I didn't care about this, right? So typically, I would say, I just mentioned, if the system, I'm not going to prove this, but I'm going to tell you, if a system A, Q, half, you should know all this notation now, right? If A, Q half, Q is the covariance matrix of process noise. Taking half means square root of matrices. Why I can take square root? Because it's it's observable. Observable, okay? Somehow Kalman filter related to observability now, okay? If it is observable, then we can arbitrarily pick x0 hat and the p0. It doesn't matter. Eventually, it will converge. Okay? We can arbitrarily pick them, not necessarily the true one. Okay? But nothing is true yet, right? If that's the case, then it will eventually converge. It doesn't matter the initial estimate and initial covariance. You can pick them arbitrarily. Okay, I'm not going to cover this. If you're interested, you can. I can point you to the right literature about this. That will take more effort to prove. Okay, any questions so far? You see, the derivation take a lot of time. The example take a very, very, very short time. I think now, without this asymptotic behavior, that's a little bit more advanced. This problem filtering step will be, I think, every single steps should make sense to you now. Okay. Now let's jump to the Kalman filter extension, so-called extended Kalman filter. To you now. Okay. Now let's jump to the Kalman filter extension, so-called extended Kalman filter. And today we're going to finish that as well, hopefully. I think now I don't need to cover extended Kalman filter even. You don't have a lecture note? Okay. Then. No online? I think definitely we'll send it to the WeChat. extended Kalman filter is maybe used more widely in applications because in reality, a lot of physical systems are not linear, okay, are not linear. But we don't need to spend as much time as we did for the Kalman filter because the principles are there. So let's state our principle first. Let's recall. Our principle is just whatever you want to estimate as a hidden variable based on some measurement, you need to find the conditional expectation. That's according to minimum mean squared estimation rule. Okay? For extended Kalman filter, or for nonlinear case, nonlinear Gaussian case, nonlinear non-Gaussian case, we still need to do this. Are you with me? There's nothing changed. The principle doesn't change. So we spend a lot of time to cover the probability and the minimum mean square estimation theory. I think all of this carry exactly over to here. Okay. And in essence, Kalman filter is just a recursive way to compute conditional expectation for linear Gaussian system, for which we have analytical formulas we just derived. Everything is accurate and exact. For nonlinear system, okay, let's look at this. Suppose we have a nonlinear system. It's not linear Gaussian anymore. So the state update equation is this is general nonlinear system corrupted by noise. Let's assume the noise are still Gaussian. It doesn't matter anymore, right? But let's assume it's still Gaussian with measurement noise covariance RK and process covariance QK. And the notation are pretty much the same. Okay. Now I'm going to ask you, in general, xk plus 1 is random, but it's no longer Gaussian. Okay, it's no longer Gaussian. We cannot use the linear Gaussian formula anymore. What we should do? Huh? It's not Gaussian. We approximate it as a Gaussian. It's just like linearization. It's not linear, but let's linearize it and approximate the dynamics as a linear dynamics. Okay, so you have seen a lot of examples. For example, not only extended Kalman filter, there are also, I think, ensemble Kalman filter, unscented. I don't know how to unscented Kalman filter. I'm not sure whether you heard about this or not. All of them are the same. In principle, they are trying to approximate as a Gaussian, but there's just different ways to approximate that. Okay? I think a little bit jump from this is so-called particle filter. Have you heard about this? What particle filter do? Using particle to approximate as a Gaussian? No, it's more general than Gaussian. It's particle to approximate the conditional density. Gaussian, if you know mean and covariance, the density function are fixed. Okay, but for other distribution, the density function is kind of very complicated, right? But I can use particles to approximate that density function. And then I can do either expectation or the maximum likelihood. Either way is fine to find the best estimate of my hidden variable. Okay, so all of them are related, and I think you have the foundation to truly understand all of them. It's just different. They differ by their particular techniques to find the approximation. Okay, let's have a quick look of extended Kalman filter. By fundamental theorem of estimation. So yeah, what is the fundamental theorem of estimation? Read the formula. Okay, is this true under Gaussian assumption or not? True under Gaussian assumption. If it is not Gaussian,
Also true.
it's also true.
Yeah. Yes, it's been proved.
It's been proved in my lecture notes, although we didn't go over them in class. Whatever distribution, I don't care. If one the minimum mean square estimate, this is the solution, conditional expectation. Of course, sometimes you don't agree on this mean squared error assumption or cost. You don't think that's a good call, you can use other things. Maximum likelihood, maximum map, maximum a posterior distribution estimate. But anyway, all that matters to compute this, we need what? Density, all right? Conditional density function. So it's xk given yk of xk given yk, for example. I need a density function. Before I don't dive into the detail of the density function because it's completely characterized by Gaussian. For Gaussian, it's completely characterized by mean and covariance. We only need to know these two things, right? But now, if it is not Gaussian, I need to know the entire distribution density function, right? So for extended Kalman filter, we're doing exactly the same thing. We just need to compute. Our goal is to compute this conditional expectation, okay? To compute this, we need this conditional density, okay? But now we are not living in the linear Gaussian case. It's no longer linear, it's nonlinear, so xk, especially xk given yk, is no longer Gaussian, okay? It may not be Gaussian. So extended Kalman filter try to approximate this as Gaussian and propagate it through linearized dynamics. How to approximate something as a Gaussian? What characterizes Gaussian, Suyan? What defines a Gaussian? What characterizes Gaussian? It's mean and covariance, okay? So it's a mean and covariance. It's a mu and a sigma, right? And this density is given. If you know these two, then if I draw one-dimensional case, it's like a bell-shaped thing, right? This is the mean, and somehow covariance determines how widely this is. Only these two parameters you can adjust. Okay, you don't have other freedom. But if something like this, let me ask Xiaohan, something like, suppose I have density function like this. This is too bad, all right? Maybe something like this. Do you think it's Gaussian? Looks not, right? How do I approximate Gaussian? All I can do is move my distribution around and scale it by this density function. This guy, right? So maybe I will do like something like this, right? And try to adjust this standard deviation or covariance parameter to find the best fit. Okay. So our rule is that. So suppose. Let's say, let's do some notation. So this guy, this guy is not Gaussian. This guy called X is not Gaussian. Okay, and I want to approximate this guy using the black one, which is X hat. Approximate X, okay, as a Gaussian. So I would say this guy will be X hat, will have a mean and covariance. Let's both call them head and hat. So extended Kalman filter try to do this approximation or it's very naturally. It's just these two things has to agree, right? So first of all, I would say we can do this by matching the two moments, or these are called moment first and second called the moment, okay, of the matching the first two moments, okay? For example, I was a male head. I want to design a Gaussian whose mean agrees with the random variable. Give me a random variable, although it's not Gaussian, I can compute its mean, okay? It's not a Gaussian, nicely looking Gaussian random variable, but I can still compute its mean. And also, sigma hat, I can compute its covariance. For arbitrary random vector or random variable, I can compute its covariance. And that is two agrees, then I don't care the rest. Okay? The approximation may be good or bad. Okay, for example, if I have a like this density function, then my approximation would be, I don't know, something like this. Okay, which may not be good enough, right? In this case, what would be a good approximation? You may have to use some particles. What does particle mean? It's like a histogram. You know histogram, 柱状图是吧? You generate a lot of distributions and using particles, the distribution of particles is like a histogram to approximate its density function. That becomes particle filter. That's exactly what particle filter is doing. Now in this class, we still do Gaussian type approximation. That's where we start talking about extended Kalman filter. Okay? So that's the key idea. The rest will be very simple. Let's say approximate the linear dynamics and linear dynamics. In this case, I can relate the previous step to the next step through the linear transformation. Let's see some details, okay? Notation are still the same. This guy is my best estimate of xk given time k, measurement up to time k, and xk given k, this is the prediction step. These are covariance, are defined exactly the same as Kalman filter, but now they are, I would say, after the formula doesn't give me the exact solution to them now. I can only find approximate version of those variables. Okay, so I still break up the whole thing into two steps. This is the prediction. This is the measurement update. Let's look at a simple case, prediction. Prediction means now I have these two guys. I have the best estimate, which is the expectation of xk given yk, and its covariance. I want to find what should be the next best estimate. All right. Let's quickly summarize the result. So for now, let's say our xk plus 1, by our model, what is it? It's fxk uk plus wk, or omega k. That's my true model, right? That's my true model, and you should be able to write down this rk, this rn times rm, because u input is rm, maps to rn. Okay, let's update my state to the next time. And I can, because I have the formula for linear version of the system, right? If it's linear dynamics, I know exactly how to update the mean and covariance, right? If it's nonlinear, I can compute, but I don't want to compute it. Take a lot of effort if it's nonlinear. So let's linearize it. So how do we linearize? That's my lecture note 2, right? You should review that. I think most of you are okay with it based on the midterm result. And so I can approximate that, linearize it. Linearize it. Around where? It says linearize around the current best estimate and the current input. So now you assume your system operates at xk hat. I just linearize my dynamics around this best estimate point. Okay, so using Taylor expansion, that will be xk hat, we'll plug in, right? And the uk plus Jacobian, right? Partial f, partial xk, given xk equal to xk hat, and the uk equal to uk. It's a function of xk and the uk, right? You plug in these two. This will be a matrix, right? Times the deviation of xk minus your operating point, which is xk hat now, plus hot, high order terms. I don't care. As an engineer, that's our freedom to ignore everything.
What about the UK?
Say it again?
UK.
UK is known. Yeah, of course. We can have that, but it doesn't matter. Let's have that. For simplicity, for completeness, we need that, okay? Partial f, partial u, evaluate at xk hat, uk, okay? This is our B matrix now. And the uk minus, no, I don't need that, sorry. I just treat it as no control input. Okay, everything is given because it's time varying. You can normalize, linearize with u as well, but you know, let's not do this, sorry. Yuntian, we don't have to do it. I only linearize by what? View it as a function of x. I don't care about u anymore. U is given, all right? That's high order terms. You will see that later. Okay, so now if that's the case, then I will say xk plus 1 is approximately xk plus what? F xk hat uk minus, let's call this guy, define this as capital Fk. It's a matrix. What's the dimension of it? What's the dimension of it? N by n. Right? I linearize with respect to x only. Okay? It's a n by n matrix, of course. So this will be our Fk. This is Fk as well, sorry. Minus xk hat. So that's the term, right? This is this term. And plus high order term, I don't care. And plus omega n, or omega k. Well, I didn't do anything. I just split these two terms. This that's just Fk times xk minus Fk times xk hat. And let's view this guy. That's my answer, okay? View this guy as my UK. Let's define this as tutor UK. First of all, I know everything here, right? At time k, I know sk hat, and I know UK, right? UK is my true input. And I can do linearization. I can also find Fk, and I also know xk hat. So everything here is known, is as a number. Okay, I call this guy UK tutor because deterministic numbers or a vector doesn't matter for filtering or for Kalman filter. Okay, that's my update equation. This may be my A, and this is my some deterministic input. Okay, this is noise. What about x? So then I can sk plus 1 given k hat equals expectation of xk plus 1 given yk. That's my hope. I want to compute this, right? This will equal to, if I substitute this in, this is equal to fk xk plus uk tutor plus omega k given yk. So because I linearize it, now I can move things out. So this will be fk times what? Expectation of xk given yk. That's xk hat. And this is deterministic at time k, so this will be uk tutor. And the expectation of wk given yk is 0. Okay? So you find out this is nothing but fk xk hat plus this thing. I'm moving it back, sorry. I'm putting it back. I just plug in fk xk hat. You see something, this guy got cancelled. And this is nothing but xk hat uk. All I did, actually this step, prediction step, is nothing but plug in my best estimate of xk hat and my current input and ignore noise. So that the prediction means basically the best prediction here is just ignoring the noise by assuming the noise is 0 and evolve your system deterministically. My question now, I don't know how much time I have. Okay, my question now is the following. So it looks we're doing something unnecessary, right? So let's say we want to find xk plus 1 given yk. Let's say without, let me do this, so-called without linearization. Let's say we don't do linearization, what will happen? This will be expectation of f xk uk given yk. Also w, but w will be 0 anyway, so this will be given yk, right? So it will be equal to expectation of f xk uk given yk. My question is this equal to, because u doesn't change, right? So is this equal to, does this equal to this k hat uk? Huh?
No.
No, why?
Because we ignore some high order terms, then they will be equal from our.
I'm not sure whether, yeah, so that's the right direction. Let me write it more clear. Can I move this in? So that means because only randomness is here, right? This part is known, I don't care. The expectation of xk given yk and the uk, and this guy will be xk hat, right? If this is true, then I don't need to do linearize. I just plug in. So the question is that. So the answer to the question is, I don't have the answer for you. No, sorry. I have the answer, but I don't want to direct tell you, but I wanted to think about this case. Does expectation of, let's say, x squared equal to expectation of x squared?
No.
If it's nonlinear now, right? It's nonlinear. This is not true in general, right? So you can now move expectation. This is what? This is a function of fx equal to what? X squared. So in this case, you can now move the expectation inside f because it's nonlinear. The only reason somehow you get this result is not because you can move the expectation in, it's because we do a linearized case, okay? If you assume a linearized model, then this is correct, okay? And once we get the linearized model, our linearization model is this part. okay? And we can directly compute update based on, so these are what we derived, right? This is our formula 1, this is 1. Okay. For the covariance case, we just use, because we have linearized model now, right? And we will just do, you see where's the linearization step? We call it linear case. The predicted covariance is AK, PK, HK transpose times plus QK. That's the update for the covariance matrix for the prediction step. And here, we just replace AK with FK, where FK is the Jacobian. Any questions? For the prediction, what we derived so far is nothing essential, okay? So the prediction step, you should somehow understand it as the following. You just plug in your best estimate at current time into your state update equation. You got your best prediction of next time. The only thing we did is plug in the best XK head to replace XK, and also assume zero noise for the process noise for the prediction. That somehow is optimal if the system is linear, and it's optimal if it's not linear. It's optimal if you assume we can use a linearized model. And the covariance step, the covariance is just this. Just replace FK, because you have a linearized model, you replace FK with AK with FK. The second part is the measurement update. This part will be even simpler. We spend a lot of time for covering measurement update for a Kalman filter, but if you understood that part already, then extend this to extended Kalman filter will be fairly simple. For this step, we have xk plus 1 given k hat, and the pk plus 1 given k. And we do the update. Before we update, that relies on linear model, right? It's a linear measurement model. So here, the only thing that matters is that now our measurement equation is, let's say k plus 1 is no longer a linear function of state. It's nonlinear, right? It's uk plus 1 plus vk plus 1. And we do linearization with respect to x. We only care about x. So this will be where to linearize it. Well, some people use different things now. Okay, so let's do. So the best estimate now is here, because we haven't do the update yet. The best guess we can have for my state is k plus 1 given k, and uk plus 1. Here will be my linearization step, okay? And the plus Jacobian, right? Partial h, partial x. This means with respect to x. I don't want to write down all the sub-indexes here. So that will be, I evaluate at x hat, k plus 1 given k, and uk plus 1. This will be a matrix, right? Times xk plus 1 minus xk plus 1 given k hat. The deviation from your linearization point, plus high order terms. Again, we define this guy as defined as what? H k plus 1. Overall, I will have what? Approximate. This guy will be. Let's call this hk plus 1. So hk plus 1 times xk plus 1. It's the same thing, by the way. So plus h xk plus 1 given k, and uk plus 1 okay, minus hk plus 1 times this guy, right? Xk plus 1 hat. Okay, plus, sorry, here there is a Vk plus 1 as well, right? So Vk plus 1 plus high order terms. That's my regrouping of the terms. Are you with me still? So now what we can do is the pattern matching, right? So let C equal to hk plus 1. That's our C now, right? This is our C, okay? And this will be our another, so this part is some constant, right? Let's call this part, match over formula here is that some deterministic part, okay? I will call it D, small d is fine, right? So at this time, everything is known, okay? Let's call it dk plus 1, some deterministic number here. And that's equal to this. And let's plug in to the formula, to the linear case, with let's say d times uk plus 1, that deterministic constant equal to our small dk plus 1, all right? So because measurement update only involves the measurement equation. It does not involve anything else. Okay, so by doing that, you can find the formula, which is, I think it's, where is it? Oh, let me copy this for you, okay? You can try to think about it later. So the best update is as k hat plus 1 given k hat plus k plus 1. The measurement plus surprise. Now the surprise, you can derive this, okay? The surprise becomes xk plus 1 hat given k, and this is uk plus 1. This is without noise, your best guess. This is what you see. This will be the new surprise. You can derive this by the previous steps. And what is kk plus 1 equals to pk plus 1 given k, that's we know before we enter in this step, plus what? No, not plus, times c, right? C transpose, which is hk plus 1 transpose times hk. Just replace ck, c with h, and pk plus 1 given k, hk plus 1 transpose plus rk plus 1 inverse. Done. Not yet. One more thing. Ki minus kk plus 1, hk plus 1, pk plus 1 given k. All right, that's our extended Kalman filter state update, measurement update equation. I'm going to post this online. I will give you examples. The codes are no longer 5 lines, just 7 lines or 8, if you know what's going on. All right, I'm going to show you 2 examples next time. One is robot localization for extended Kalman filter. Another one is joint state estimation and parameter, okay? Morning, everyone. Let's get started. On Monday, today is Wednesday, right? So only 2 days ago, we start talking about extended Kalman filter. I think I was pretty much in a rush at the end of the last lecture. And several students asked me a few questions about the derivation of extended Kalman filter. I think most of the question is concerned with the fact that I didn't linearize about U, the control. I only did linearization for the state. Okay. We can do linearization about the U, but I don't think that's necessary. And let me explain why that's not necessary. Okay, last time I think this is not equal to that, right? That's the reason we need the linearization for X. If you look at the linear formula for, so Kalman filter or extended Kalman filter both involve two steps. Okay, one is the prediction step. The other one is the measurement update. So the prediction step, you can see, let's look at the other more. Let's just look at this loop, all right? So that's all about Kalman filter. All the formulas are here, all right? So my question is that we often, we assume throughout the semester for linear system, and in the linear system is of the form AX plus BU, right? And in Kalman filter, we add some noise. So that linear system is linear in both control and state, right? It's linear in X and also linear in U. That's our assumption throughout this semester. But for Kalman filter, I don't think we need a linear assumption for control. For example, let's say example, suppose my system is AXK plus, for simplicity, let's consider scalar case, okay? Let's say UK squared. Can we use Kalman filter? Let's say, of course, we have noise. And the measurement is the same thing. Let's say we have CXK plus e to the UK plus VK. Suppose this is our system, and do you know how to do, can you still use Kalman filter?
Yes.
What's the, you look at the formula, okay, what's the role it plays for the control? Control is deterministic. It doesn't matter what it is. You always subtract it out or plug it in to help you to predict. And the way, so first of all, the question I'm going to ask is X and the YK are still Gaussian in this nonlinear, linear in state, but nonlinear in control case. I'm asking you, is this XK, let's say XK is Gaussian, WK is independent also Gaussian noise, and VK, all the noise assumptions are still kind of assumed. But it's just the difference is that UK, instead of some number times UK, I have a nonlinear function of UK, and it's UK squared. Okay, UK is deterministic. Okay, so I ask you, is this XK plus 1 still Gaussian? Yes, right? It's a linear mapping or function of a Gaussian. This kind of deterministic number doesn't affect its distribution. It's affect the mean, but it doesn't affect whether it's Gaussian or not. You see what I mean? Okay, so it's still Gaussian. So the linearity is trying to make sure that all the state and output are jointly Gaussian, but that's true for as long as A and C are, the system is linear in state, and we don't require it to be linear in control. I'm not sure whether that explained it. I can further assume. So this is equivalent. I can write it like I let, in this case, it's, let's say I would let U tilde K equal to a vector, let's say UK squared and e to the UK. okay, I define this U tilde k. It's still deterministic, right? Because you know UK is deterministic, and the function of deterministic variable is still deterministic. And this UK tilde is deterministic. And I don't have space, okay? Let me do this jump here, sorry. So in this case, I would say my system will be equivalent, it can be equivalently written as AXK plus 10 UK tilde, okay? Plus noise. And the YK is CXK plus 01 UK tilde plus VK. Are you with me? I can do whatever transformation I want for deterministic input. Okay, it's still deterministic. So once you know UK, you can compute UK tilde. So UK tilde can be viewed as an artificial input to the system. And now you transform the nonlinear in control case system to a linear case that we are dealing with, right? And you can apply exactly the Kalman filter formula we gave you here. Okay, so you can imagine this nonlinear function can be arbitrarily complex as long as it only involves control, because control is deterministic. Then it doesn't affect the nature of the state. The state is still Gaussian, and also Y. Any questions? So this is the fundamental reason that I didn't linearize about U, because I can leave whatever linearity there. It doesn't affect my, so you can see I put whatever I deterministic at that time k as UK tilde, and that changes to the linear case. Okay, so that's the reason. Hopefully that answers your questions. Any further questions? Okay, let's, I think everything is not hard. It's just you need to linearize about the state, okay? Linearize the state around the best estimate of the state at that time. Then you evolve your filter. Okay, so I think the best way to learn it is to look at examples. Let's go back to our localization example. That's a toy example, but also give you somehow a perspective about how the system, how Kalman filter can be used. We have done this example in the nonlinear nonlinear least square case, right? You can use nonlinear least square to estimate the location of a vehicle. Let's say my car or robot is here. And so in the environment, I have a map, okay? That means I have some kind of markers with known positions. Here I call the beacons, all right? So I can only know the distance. Any given time, I have a measurement, and my measurement is the distance between the robot and the corresponding beacon. Okay, if I have 4 beacons, I have 4 measurements. And that 4 number tells me how far I'm away from each beacon, and plus some noise. Okay, and I'll call this PK, right? PK is the position or robot location at time K. So my question is that how do I use my measurement and to estimate my position? So the question is, the goal is to find the best estimate my location given the measurement this. Of course, something is known, it's the position for the beacons are known. Any questions? Okay. The nonlinear least square case that we kind of studied or learned for lecture 3, I think, right? And that's for instantaneous. Every time step, I do a new kind of estimate based on one shot measurement. So k times, let's say current time is k, I only use measurement at k steps. I didn't kind of consider all the measurement history, right? And the Kalman filter allows us to do the best estimate of this precision given all the measurement up to time k, and it's optimal in the stochastic sense. Okay, how do we start? Is this a Kalman filter problem? Okay, if you in real life, you will not see a Kalman filter. Your problem, you will not be given a problem that tells you A, B, C, D noise, and then ask you to do an exercise. That only happens in the exams or in the lectures. Okay, in real life, you are given a concrete problem like this. I want to know the precision of this, and you need to know how to connect the application to the fundamental nature of the problem. The fundamental nature of the problem is what? It's trying to estimate something you don't directly measure. You don't directly measure the location, okay? You measure a few things. You want to use those measurements to estimate the hidden variable, pk, okay? That can be done in the deterministic case, the least square problem. But in the stochastic case, that's an estimation problem. If the estimation problem involves kind of a sequential correlated measurement, then that's a Kalman filtering problem. All right, that can be viewed as a Kalman filtering problem. Okay, so let's see how we can. What's the system model in this case? It's up to you, by the way. As I mentioned at the very beginning, all models are wrong, right? Some are useful, and what's your best guess about the system model? Or what's the assumption you want to impose to help you understand, to better estimate the precision? Typically for tracking, let's say, if you don't know how the people drive his car, or how the robot is going to move, and a commonly adopted assumption could be, okay, there could be others, could be constant velocity. It doesn't mean the car has to travel at constant velocity. It just means it's within a few time steps, its velocity doesn't change that much. Okay? If that's the case, then you can somehow impose this assumption. So our assumption here is model assumption. It's a constant velocity, constant speed assumption. What do I mean by that? So velocity, so p precision dot equal to constant. Is this a linear system? Well, you don't know, right? I mean, let's see. I mean, what does this mean? This means, let's call it, this velocity is given, right? It's called S, and this is in R2. Velocity on the plane, okay? It's R2. This is a given constant. No, not given, but unknown, sorry. I just know it doesn't change over time. Okay. And then I can take another derivative that tells me the acceleration is 0. Let's have more information. This is superficial or artificially imposed assumption to help you to make sure your estimate can help you estimate if your measurement is pretty noisy. Okay, so let's define our system dynamics. Okay, let's define our xt. It's constant velocity. Let's assume the continuous time system to start with. Then we can discretize with a different sampling time. Okay, this is a pt. This is a p dot t. This become R4, right? The state has my assumption, my modeling assumption. If I assume constant velocity, that's my model. Okay, you see how I translate a somehow assumption to a model. This model is a linear second-order differential equation, so we can write this as a linear system, right? ABCD thing, right? So then I can say xt dot equal to pt dot pt double dot. This is times identity. This is 2 by 2, right? Block 0 0 times pt and pt dot. This is my dynamical system, and this is my A matrix. Looks particularly simple, right? Very simple with only here corner have a 2 by 2 identity matrix. This is our continuous time system AC. You should be very familiar now how to do a linearization, especially the simple one, the Euler linearization. So transform to dt, discrete time model, with delta t as my sampling interval, all right? And so you should be able to write it down right away, right? So k plus 1 means the x at time, k plus 1 times delta t, right? Equals the previous time location or the state plus the velocity at the previous step, which is x dot, right? This part. This will be 0i 0 0 xt times delta t. Okay, so that will be this will be a identity that's plus here. That will be identity times delta t. This is 0 times xk. Okay, this I call it AD or A. Okay, if I call this AC, then this is my A, it's fine. So these are 2 by 2 matrices, 2 by 2 identity matrix. Right. What about measurement? This is my modeling assumption. My assumption could be wrong. You may disagree with my assumption. Okay, that's fine. But this is an assumption we somehow feel it's reasonable to assume that over a few short time that the vehicle doesn't change that much. All right. And the measurement is the distance to the beacons plus some noise, right? So that will be, let's call it YK1, YK2, or YK3, YK4. In this example, we have 4 beacons. And by definition, this is the nonlinear function of the state now, right? So it is, let's call it HI xk means, so I have to write my output as a function of the state, okay? So the S component of the output is square root, the distance, right? This distance, let's call this distance. So it only involves xk. Xk has 2 parts, right? R4, the position part and velocity part. So sk1, sk is a vector. sk1 minus the beacon position b1, the ith beacon position, suppose I do this, squared plus sk of 2, the y coordinate of the robot position minus the y coordinate of the ith beacon squared. Take square root, that's your distance. If my state is here, it's distance from the ith beacon. And this distance doesn't depend on x3, xk3, and xk4 because that's the velocity. And now we only care about location. So if I define this kind of a notation, then I can say this is nothing but xi of k, x1 of k, x2 of k, h3 of xk, h4 of xk. Function plus some noise. Noise is also, its beacon have different noise. 3, 4. Okay? This looks more like a nonlinear function of state now, right? Let's try to see, can I use Kalman filter to do the estimation? No, right? Because it's a nonlinear function of state. If it's nonlinear function, it's only nonlinear with respect to control, then I can do still do the linear Kalman filter case. But it's a nonlinear function of the state. I have to do extended Kalman filter. Okay, for EKF, so we can use the following model. We can use the following model. Xk plus 1 equal to AXK. That's our modeling assumption, right? That's AXK, that means it doesn't change over time. But I can add some noise term, okay? Indicate that I'm not so sure about things, my modeling assumption. I allow a little bit uncertainty about my modeling assumption, okay? As I mentioned at the very beginning of a Kalman filter, the incorporation of uncertainty is so important. Being arrogant is the most dangerous thing in your life, okay? So this is, I would say, noise term can be added to account for deviation from the constant velocity speed assumption. Okay? If you're so sure it doesn't change over time, then I think you'll be wrong, right? And if, as long as you deviate from that assumption a little bit, your estimate will be very, very bad, okay? So yk is h of xk plus v of k, okay? So that's my model. I don't have a control. If I have, control or deterministic control input doesn't affect nature of Kalman filter. We can very easily consider that if we have. Or in this case, it's just a uncontrolled autonomous system estimation problem. Okay, now we can do the estimation for x given measurement. To apply Kalman filter, let's do one more extended Kalman filter. Here, the only nonlinear term, do I need to do linearization with respect to the state update equation? It's already linear, we don't need to do anything, all right? For the extended Kalman filter, we need to do this linearization with respect to the state measurement equation, right? So that's our fk. Okay, our fk, we don't need to do linearization, or the linearization trivially given, right? Our fk is just a, and our ck, at any given time, I have a C matrix, should have a C matrix, would be partial h, partial x, evaluated at x hat of k. Okay, should be k plus 1 given k. I think, if that's the k, then I can use this k given minus 1. All right, that's the best estimate of your state. Given all the past history, I want to linearize my measurement around this case. Then that will be partial h. H is a vector, right? Function. So h h1 divided by partial x1, partial h1 divided by partial x2, all the way to partial h1, partial x4, and this is x1, yes. Oh, sorry, I think that's wrong, right? That's wrong. The first one is all x1. This is h2, partial x1. This is a partial h4, partial x1. Now it's partial h1, yes, 1 partial x2, okay? I have a 4x4 matrix, and I need to evaluate the thing at a particular the best estimate. Okay, once I know this, that's my HK, by the way, in the formula, then I can use my derived equation to do the, just see this equation, right? Prediction is this. This is the measure and update part of the system. And for the prediction part, I think it's oh, I summarize here, right? That's the prediction stage. Okay, let's look at the example. Any questions so far? Why we assume constant velocity? We don't know anything, right? So if you use the, I think, I'm not sure the current, if you use the app, the navigation app, right, they will locate your car position. So sometimes they ask you to take, they may ask you to go straight, but if you take the exit at the highway, right, because the app assumes you go through constant speed, all right? You're traveling on a highway, suppose, right? And there's an exit. You all of a sudden take the exit, you go out, and they will still assume you're on the highway. For a few times, eventually they switch, they realize you are there, right? So the behavior of that is just because they assume a somehow constant velocity, or you assume you follow their directions, that their assumption imposed on you, right? So that's the way of using Kalman filter. That's typical assumption to do tracking. This example is maybe the only case I'm still using MATLAB here. Okay, I didn't get time to convert it into Python yet. So let's just take MATLAB. I hope everyone will like MATLAB better. So this is, let's see, localization example. What I'm doing here, I did a simple GUI to draw a box. Let's not worry about that first. And here is the beacon position. How many beacons I have, it depends on how many columns I have. So those are beacon position. Each column, it's the one beacon position, the planar coordinate of its beacons. Okay, you can arbitrarily choose the number of beacons you have. And then I plot them on the figure. Suppose I run up to here. Hold on. Those are the 4 beacon positions. Okay. Then let's see. Initialize the simulation. Let's start initialize the simulation. Those are kind of a setup work. And that's my sampling time. All right. So initialize Kalman filter. I would say extended Kalman filter in this case. Again, I can randomly guess where my location is. X hat is not the true location. And n equal to 4, that means the dimension of the state is 4. M is the number of beacons. In this particular case, I have 4. This M should be 4, okay? Those are initial kind of a covariance matrix. Have a noise variance. So this part is I'm somehow using the mouse to to direct where I need to go. Let me run this first. You have some kind of, so if I do start, no, hold on, stop. Let's run it. This is the initial where I am, okay? If I do start, then my Kalman filter is estimating, okay? Because the sensor is noisy, so my estimates will always keep moving, right? Because each time the measurement I receive has some noise. It's keep changing. And this circle, this is the ellipse or ellipsoid, is so-called confidence ellipsoid. In Kalman filter, and because of the Kalman filter level set, or confidence is a quadratic function less than something. And if you read my tutorial on geometric linear algebra part, and that's how to represent ellipsoid, the ellipsoid can be represented as the level set of a quadratic function. If you need to know more of this, I can direct you to the right source of the literature. If I use a mouse, then this guy will move, all right? This robot, I can control it. It doesn't need to be constant speed, and I keep tracking it, right? And if I go to this corner, let's click here, it will move to here. You see the ellipsoid, it's like this. Let's do here, join, okay. So what does this mean? Is that you see this semi-axis direction. Along this axis is more noisy, or more, my confidence is more variance along that direction. Along this direction, I have less variance because of the location of those vehicles. That determines my confidence or the uncertainty about the estimate, okay? If I move to here, eventually they will, you see it's almost circle. You see, if I in between of these two things, along this direction, the confidence is a little bit more, or uncertainty is less. Okay, that's the GUI you can play with. I will upload it to the website. What essentially we are doing is just a few lines of extended Kalman filter. This part doesn't count, okay? I'm just trying to take measurement. The measurement is just the current position of the vehicle, the true position. In reality, you don't generate the measurement by yourself. You receive a measurement. Okay, here for testing, we generate the measurement by ourselves. This is the distance between my position and the beacon, and plus some noise. The reason I have square root is because I want to make sure that the noise covariance is what I specified. Okay, this part is so EKF update. What does this function mean? It's nothing but from here, xk hat, pk to xk plus 1 hat to p plus 1 hat, the whole thing, right? The prediction and measurement update, two-step, I group that into one function. That's the essential part of extended Kalman filter. If you look at this EKF update, these few lines are just setting up the parameters, and the essential part is just few lines. Okay, and this is H is the linearization matrix H, right? If you do the linearization, I can derive the formula. You plug in that formula, and that will be the result. And this is H without noise is like this. It's the, if you look at the update equation, measure update equation, this part, okay? That means without noise, you assume your measurement should be something, but your measurement tells you something else. That's the surprise term, right? And times the Kalman gain that gives you the best estimate. So this is this is Kalman gain. This is the predict plus Kalman gain times the what? The surprise. Then that's it. Okay, that's a whole example of the tracking, right? From here, you can do a lot of things, even SLAM. Okay, there are different versions of SLAM, and you can use EKF or Kalman filter type of tools to derive SLAM, simultaneous localization and mapping. Okay, Any questions for this example? Another kind of very important case Kalman filter can be, or extended Kalman filter can be used, is to do joint state and the parameter estimation. This is the part I'm going to talk a little bit today as well. So my question is the following. I have a system. Suppose, for simplicity, in this example, I have a system of second-order continuous time system. Okay, so this corresponds to the transfer function is what? Omega n squared, s squared 2 zeta omega n s plus omega n squared. Standard second-order system. Okay, there could be, I mean, those are parameters, and so-called damping ratio and also natural frequency. So if I want to use state space, okay, then I have a state, it's x and y and y dot, and the parameter is these two things. Okay, for this square problem, we studied the case of yeah, we can use least square to estimate this, right? And we didn't consider formally about measurement noise. Here I want to say, if I have a linear system, nonlinear system, so the parameter is also unknown. This is unknown, and the state is also unknown, right? I can only take a measurement about y. So how do I do the joint state and the parameter estimation? So that's the question I'm going to tell. So let's consider a little bit more general case. And the x dot equal to fx, u doesn't matter that much, okay? Theta in this case is a parameter of your system model. In this case, is this. In this case, it's a linear function of state and control, but in general, let's consider a general case. Plus noise. Okay, that's noise. And y equal to h of x and theta. U and theta, u doesn't matter. V of t. Suppose that's my system, and this is a system parameter. This is the parameter of your model that you don't know for sure. Okay. So the goal is to use the input up data. Input you know, and output you can measure to estimate theta and xt. Okay, x and also state. So it's called the joint parameter and state estimation. So if parameter is given, you can use these two to estimate state, right? That's Kalman filter or extended Kalman filter can do that. But if theta is unknown, typically the model is somehow unknown to you, right? Or you need to somehow derive it, and you're not certain, or you're not sure about the parameter. In such a case, you hope the measurement can also help you estimate or validate your parameter as well. Okay, so what we can do is that step one, we can view, that's the key, right? We can view parameter theta. So Kalman filter is used to do what? State estimation, right? And we can put everything unknown as a state. Okay, we view theta as a state. Okay? It's a constant. Why it's a state? It doesn't change, but that means it doesn't involve any differential equation, but I can impose artificial differential equation, which is theta dot should be 0, right? That's a differential equation. That's a constant assumption. plus, as I mentioned, you shouldn't be so sure about your assumption, plus some process noise, which I call omega theta time t. Okay? Is this fine? This will allow your model to modify theta. Otherwise, you're so sure it doesn't change, then it doesn't really evolve. This is a artificial, not intelligent, artificial imposed, okay, to allow the estimator to modify the theta value, okay? Or I would say to account for, just like before, to account for deviation. I think in this case it's not deviation from constant assumptions. It is indeed a constant in this case. It's just to make sure my estimator can update it, all right? Now we have a new state, so-called extended state, right? So that new state will be, I would say, approximately as, let's just define it, not approximate. Define it as xt and the theta t. Okay, that's my new state vector. State dimension got increased. Now xt dot equals to, first of all, does it depend on the state dimension? This is Rn, and theta can be one or multi-dimensional as well. So that will be my x dot t, which is my vector field, which is f x u and theta. Okay, theta is a part of the state, so I can put it here now, right? If I call this x, this is, I don't know how to note it, just call theta is fine. And this part is 0, right? The second part is 0, theta dot is 0, plus some noise, which is the noise associated with x, and the noise we superimpose, artificially imposed for theta. And I can call this guy my f tilde, x tilde u. Where is the theta? Theta is here, right? This is x and theta. So this guy is a function of the extended state vector and the input only. And the plus omega tilde thing, right? That becomes a standard nonlinear vector dynamical system. And the yt is h x tilde. I can have u as well, and this is my v of t. It doesn't change. Which step? Let's call it step 2. No, step 1. Okay. Step 2. Now I can do discretization. Discretization with delta t. Then I have x tilde k plus 1 equals xk tilde plus f tilde xk tilde uk delta t plus, let's assume we have some noise here, and yk tilde is, not yk tilde, it's just yk, it's hk tilde u vk. So this will be my nonlinear function discrete time, okay? Nonlinear function here. Now I have a standard setup of extended Kalman filter that I can use to jointly estimate, to just estimate xk tilde. Xk tilde involves theta. All right, we're done. So we derive the most general case, then you can use extended Kalman filter to do it. For our example, let's go back to the example. For example, today I'm going to assume some simple case. For simplicity, let's assume we somehow know ahead of time. Let's assume we know the natural frequency we know is 1. It's known. The only unknown is what? It's the state and the damping ratio. It's the zeta. So in this case, I will have x1. The state is what? X should be x1, x2. What else? It's zeta, okay? It's in R3 now. 2 state vector, which is y and y dot, and 1 parameter, which is unknown, it's zeta. Omega is known, all right? So now we know x dot equal to x1 dot equal to x2, because that's y dot. Any questions? 什么问题吗? Don't trust my derivation, just you should always question, because I make mistakes all the time. Any questions? This is y, this is y dot, okay? And x2 dot, which is x2 dot is y double dot, right? If you look at this assumption, y double dot is this guy moved to the right. And so if I write it down, will be, that's what? Let's not do this continuous time. Let's just directly do the discrete time here, okay? That's xk plus 1. I'm not sure whether you can see this or not, okay? This is x1 k plus x2 of k times delta t. My notation has somehow changed. Let me be consistent. That's xk1, xk2, delta t. Let me finish this part. We'll take a break. Then this xk2. The second coordinate is plus, this is the vector field times delta t, right? The vector field now becomes negative omega n squared times x1, which is, this is 1, right? So it's xk of 1 minus 2 zeta, omega is 1, so this is x2, xk of 2, plus u times delta t. This is uk. Okay, now this guy, the third one, sorry, this is state. It doesn't change, okay? And then plus noise. I'm jumping one step only, okay? I do the linearization already here. This is the velocity times the time interval. This is the current, the previous step, location of the state, component 2, times the velocity, times this. Why is this? It becomes omega n is 1. So you look at this part. If you move these two guys to the right, this is uk, right, minus 2 zeta x2. This is x2, right? And minus omega n is 1, right? So minus x1. So that's where, so it's minus xk1 minus 2 zeta xk2 and the plus uk. This whole thing is the velocity, the speed of change of the second coordinate times delta t. Okay, we'll continue next lecture. Okay, let's continue. Here's some typo here, right? So this is x2. It's the x1, x2 plus the parameter zeta that we want to estimate. Okay, here is x tilde as well, but x k2 and x tilde k2 is the same. The only thing that x tilde differs from x is it has a third component, which is zeta. Okay, that's my differential equation. Sorry, the dynamics. I can call this guy. Let's call this guy is our f x k. Do I have u? Yes, uk. Okay, is this nonlinear?
No.
It's nonlinear, right? Because zeta, I should.
Oh, yes.
This guy should be x tilde, right? xk3. So the only nonlinear term is here. All the other terms are linear, right? So it's nonlinear, we have to do in linearization. We have to use extended Kalman filter. I think that's easy to do linearization for this one, right? So you can say f k, so at any given time, the linearized A matrix, which we call fk, is partial f, let's see, partial f, partial f, partial x, okay? And evaluate some best estimate place, right? So, but let's derive this formula first. That will be, it's a 3 by 3 matrix, right? Its state is dimension 3. So it's partial f1, partial x1, which is it's 1. The only thing related to x. Well, can you see that? I mean, I don't have to write partial xk plus 1, right? I mean, that doesn't. This is a function of these two things. The first few coordinates, we call it x, right? You can plug in xk or xk plus 1, but f is a function of those variables. And partial derivative means with respect to this x coordinate, x vector. So partial f, partial x2 is delta t. So partial f, partial x3, the first row doesn't involve any x3, so it's 0. Okay. So and partial f2, this second row, x1, so this is negative delta t. Okay. Partial f2, partial x2, which I think this is notation. This is 3, right? Okay. So first of all, I have 1 here, right? So it's 1 minus 2 x3. Let's call it x3 now, okay? Let's call it xk3 if you like. xk3 times delta t. All right. And then I need to move this further. And the second one is, what about x3? x3 only this term, so it will be negative 2 x2 k of 2 delta t. Okay. Okay, that's my. The third row is 0, 0, 1. That's my linearized model. At any given time, linearized A matrix, which we call F here, right? Fk change with the state. And we plug in the best estimate at that time to use that to estimate to do the Kalman filter. What about Y? Y is linear, right? In this case, in our case, y is what? 1, 0, 0 times xk tilde, right? The only first coordinate, because we call this y, right? You see that? Okay. Let's try with examples. Well, what's going on? What? Removing previous version. It got restarted. This is the example we covered last time about this Kalman filter. Let's look at this extended Kalman filter. Joint state parameter estimation. This example, right? Omega n is 1. I assume it's 1. But zeta, here I can impose anything I want. For example, I can say zeta is 1.5. This is A matrix. That's my original linear system. Okay, I'm trying to simulate. I'll say it's simulate the true system response. Okay. So how did I do the simulations? I have a discrete time. I do my simulation by myself, by the way. So I put in my control to generate data. I treat my control as a sinusoidal kind of functions. I gave an input. So the output is a linear system. The output should also be sinusoidal. And if I plot it, let's clear out all the cells. Let's run this cell. That's my kind of output. So you measure the output, you also know the input, right? For example, if I don't do this, let's say let's do a step response. Let's say 2 times, just 2. Okay, that means you have a constant input 2, right? You should have a standard kind of linear system response like this. Because I initialized all the y to be 0, so the last one I didn't assign value, so it's still 0. So you don't look at this part. All right. If I want to say this is let's not worry about this. This particular value doesn't matter, right? I just simulate up to 1099, 999, right? That should be the case. Let's say we have a richer kind of input so that I have a better kind of more data. And then this is part of the state and the parameter joint estimation. Let's see what I have. 0, that's my initial guess of x hat. This x hat is my x tilde hat. Okay, that involves x and also zeta, right? That's 3 dimensions because x is 2 and plus 1. Right, the 3 dimension. I somehow kind of have a process noise. I can artificially impose. You can tune those numbers later on. And this is the third row, third column that correspond to the covariance I artificially impose for the parameter. I'm not sure whether you know what I'm talking about. Let's go back to the lecture note a little bit. That's this one. Okay, in this example, of course, this is process noise. This is the theta noise, right? And I somehow want to tune this a little bit smaller, okay, because I somehow assume this is really constant. Okay, I can make it bigger. It doesn't matter that much. Then I can do the update. Only a few lines, just these few lines of code. And this is a prediction step. And the first one I'm doing is what? The F, this is the linearization, right? This is F, compute linearized A matrix, which is F here, okay? This is what? This is this formula. Can you see that? 1 delta t, 0, and negative delta t, those things. And you can see that it's 1 delta t, negative delta t, 1 minus 2, x3, whatever. Okay, you plug in the best estimate. You see that? You plug in the best estimate at the time. That's my linearized model. Okay, then I can do the prediction. This is the prediction. But how did I do the prediction? It's this according to the model, right? So this is f. I just plug in xk hat at time t, right? So this should be, I think this should be, I think this should be xk tutor, right? So that's my joint thing. I just plug in the best estimate to that formula. I will upload this later, then update my kind of a covariance. And the measurement update is the same thing, and this h, I don't need to do linearization because h is linear already, and that's how I do it. Okay, let's see if I run it. It tracks pretty well. This converges to the third one is what we really want, okay? The third one is somehow convert to 1.5, all right? If I change this to parameter I didn't know, right? So parameter 1.5, let's say send to 0.9. I run it again. It somehow converts to 0.9. In this case, somehow it's able to converge. I don't think it converges exactly to 0.9. Okay, if I zoom in the figure, you may see it's a little bit have steady state error. It's possible. We cannot guarantee anything that converges exactly, but in this case, it go roughly in somehow give you a way to converge to a good estimate of the parameter. Okay, with that, I think you have learned everything you need, at least for this class, about Kalman filter and extended Kalman filter. Okay, any questions so far? I spent a lot of time deriving and teach you probability. I don't think it's necessary to do exercise, but it's necessary for you to go further and deeper to the topic. All right, some people, advanced students may already feel a little bit boring, but that's I like, okay? If you feel boring, that means you understand everything. I think that's kind of important. You may have heard a lot of other filters, right? Asymptotic Kalman filter, ensemble Kalman filter, particle filter, even Bayes filter, a lot of those terms. And with our coverage of probability and the way I teach you Kalman filter, you should be able to do all of them. I don't want to teach you everything about that because we don't have enough time. The key thing I want you to maybe remember from me is that all this filter is based in base estimate. All that cares is your conditional distribution. Okay? Kalman filter is just one special case. The key is to compute conditional distribution. For Gaussian, the distribution is characterized by the mean and the covariance, so we keep them. Then we know everything about distribution. For other distribution, it's not characterized by the mean and the covariance, so you have all different ways to approximate this. Okay, if you know what's going on, those filters, whatever fancy terms you may see from the textbook or online resources, majority of them are concerned how to compute or estimate or approximate this posterior, posterior or so-called conditional distribution. Okay, if you keep that in mind, I think you can do a lot more, but I don't think we have the time to cover all of them. I think that's good enough. Let's jump to the next very important topic finally.